Anand, can you quickly turn on your video and mic?
Yes, sir. Good afternoon.
Yeah, good
I
afternoon.
have turned on the video and mic.
Yeah, so I'll make you co-host and then maybe you can check if your screen sharing works.
Sure.
Yeah, you are co-host, so you can check if your screen. Can you share your screen? Yeah, it's okay.
Is it working?
Yes, I can see your screen.
Okay.
I can see your screen.
I'll just turn on the slide view,
Yes,
presentation view. Is it still good visible?
yes, this is visible. Yeah.
Okay. Okay.
Okay, so we are all set. We'll just wait for a few more minutes and then I think the YouTube streaming has started. We'll wait for a few more minutes and then start.
Okay. Now should I stop sharing now?
Yeah, please stop sharing.
Okay.
Okay, we'll just wait for a couple of more minutes before starting the formal session. We'll just wait for a couple. Okay, welcome everybody to the second day of the 6th Indian SAT and SMT Winter School. Uh, so today we have 6 short talks presented by researchers who are actually we may end up having 5 talks because we haven't received confirmation yet from the last speaker. These will be presented by researchers who are doing work in various areas and also use SAT or SMT solvers as part of their research. And after that, we are going to have an invited tutorial by Professor Marian Hule from Carnegie Mellon University. So that is going to start from 5:30 p.m. Indian time. That is roughly 2.5 hours from now. But before that, we hope to have a lively session with these short talks where researchers are going to talk about their work. So we will begin with the first talk by Sumant Prabhu. Uh, he's a PhD student at the Indian Institute of Science, Bangalore, and he's also a researcher at Tata Consultancy Services. So Sumant, if you could share your screen and start your presentation. Sumant, can you share your screen and start the presentation?
Thanks, Supratik. I hope my screen is visible. I'll
Yeah,
be
we can.
giving I'll be giving an overview of our recent paper, specification synthesis with constraint on clauses. This appeared at PLDI 21, and it is done in collaboration with Professors Grigory Fedyakovich, Kumar Madhukar, and Deepak D'Souza. Consider the problem of program verification. You are given a program and an assert, and there is a condition in the assert. You need to check whether all the states that reach the assert satisfy the condition in assert. To illustrate the problem, let us look at very simple program. Okay, so here there is a variable x that is getting initialized. Then there is a loop that has non-deterministic loop condition. That is, we do not know how many times the loop is going to execute. And in it, x is getting decremented. And once the loop exits, we want to check whether the value of x is always less than or equal to 19. Right? So you can see that since x is 19 to begin with, and we are assuming that x is a mathematical integer, so x is always going to get decremented, so x will be lesser than or equal to 19. But how do we prove this? Right? So to prove this, one can find an inductive invariant. An inductive invariant, you can kind of inductive invariant will give you the over approximation of all the states that are reachable at loop head. Okay, so you can consider it as a function which maps the values of x here. Right? There is only one variable x here, which maps the value of x to true or false. Okay, so it is a relation over one variable. Okay. And along with that, it has to be over approximation of all the states that are reachable at loop head, right? So for that, we need to make sure that it consists of, we'll kind of assume it to be a set. So it consists of all the states that are there in the beginning, that is x equal to 19. And if you take any state from the invariant and execute the loop, it has to, whatever the state that you get, that also should be there in the invariant, right? That is, it has to be closed with respect to the loop's body. Now, also it has to be disjoint with the negation of the condition, or it has to be a subset of the condition that is there, right? So x is less than or equal to 19. So you cannot have an invariant that consists of, say, x equal to 20 and it to be a safe. Okay? So for instance, in this program, we can have this inductive invariant that is x is lesser than or equal to 19. Okay. So how do you solve such problems of inductive invariant inference? So one way is to encode them in this logical system called constraint Horn clauses. Constraint Horn clause can be of any of these three forms. It will be over a set of uninterpreted relations, which are denoted by R here, and it can have concrete formulas, which are denoted by phi, right? So interpreted formulas. And these formulas will be over some set of variables that is denoted by x vector x, right? So it can be of any of these three forms called fact, inductive, and query. Let me illustrate this form with respect to the previous program and the inductive invariant conditions that we had, right? So the first condition that we had was the initial set of states, right? That should be there in the inductive invariant. Okay, so let's say we are representing the inductive invariant with the relation I and V is over x. Let's say x is the program variable that's there, so V is over x. So the initial state should be there. So x equal to 19 should be there in invariant. Okay, but in the initial condition may be any other formula also. Say x is greater than 19 or anything. So for all x, for all that value should be there in the invariant. Okay, so it is for all x equal to 19. Invariant, it should be there in invariant, right? So this is the general form, right? So this is the general form that we referred as fact earlier, right? So the general form is for all x or some set of variable x, there is a interpreted formula phi that should imply an uninterpreted relation R. R here can represent invariant. And the second one, right? So the second one here, the invariant should be closed with respect to loop body, right? So you take invariant and you take any any state in that invariant and execute the loop body, right? So say x minus 1. So you save that in a new variable, it's x prime. So now whatever value that x prime can have, that should be there in the invariant also. Okay, so it should be for all x and x prime, invariant of this should imply the invariant of x prime. Okay, so that is the general form of this is the inductive clause that we had. So on the left hand side, there can be one or more uninterpreted relations, And on the right-hand side, there will be one uninterpreted relations, and the left-hand side can also have an interpreted formula, right? So the loop body, for instance, in the previous case. The third one is what is called as query. So query is, you have the invariant, right? So invariant has to be disjoint with the negation of condition, or invariant has to be a subset of the the condition, right? So for the that can be represented as invariant of x should imply the condition x is less than or equal to 19. Okay, or a more general form. So we may have multiple uninterpreted relations. I'll come back to when we can have multiple uninterpreted relation, but in this case there was just one uninterpreted relation. But in general case, you can have more than one uninterpreted relation on the left hand side. This should imply an interpreted formula. Okay, so if these formulas, we'll assume they are from a fixed theory. Okay. Uh, so now what do we when do we say we have a solution for CHC? Right? So you are given a set of CHCs, and each CHC is of the form that we saw earlier. Right? So you are given a set of such CHCs, and say they are over some sort of relation R. Okay, R consists of some finite relations R1 to R plus 1. Now we call a solution the solution is a map that maps each of this relation to a predicate from some theory, which makes, if you substitute the relation by the predicate, it should make each CHC in S valid. Okay, so such a mapping is what is known as solution for CHC. For instance, the previous one, right? So if you find an inductive invariant that, if it is actually an inductive invariant, then that is a solution for the CHCs that are representing the invariance condition. Okay, so we have been working on, given a set of CHC, how do we solve these CHCs, right? So the CHCs can be represented, can represent different types of program. Perhaps it can represent a program that is having single loop or multiple loops, or even it can have, the programs can have arrays, right? So for each of them, we have certain techniques to solve these CHCs, that is to find a solution to this given system of CHCs. Our recent work is addresses this problem of specification synthesis, which can appear in multiple applications, and one of them is this open program verification. Okay, so open program verification. So earlier we saw a program and an assert was there, right? So in program, there can be a statement where a function is getting called, but we may not have the function's body. Okay, so the function's body may not be implemented, or it is not yet available, or it can be any case. Right? So a typical is, you are writing a kernel perhaps. Okay, you are writing an operating system kernel, and there maybe you are calling a device driver, and device driver is not yet written. It is written maybe later on by the hardware, hardware, whoever has hardware. Right? So such cases, right? So you may, you will have function calls, but you do not have the body of the function. Right? So now, under what constraint or under what specification for this F, and all invariant and all, do we have that assert is still, the condition in assert still satisfies? Okay, so this is the open program verification, and this problem is known as specification synthesis, and it appears in other applications also, like safety games, compositional verification, and so on. Right? So functions, that is uninterpreted functions. Right? So can you find quality specifications for this function such that these conditions are met? Okay, so that is the problem of specification synthesis. Okay, or more concretely, let us look at a modified version of the simple program that we saw earlier. Right? So now again, the first two blocks remain same. So x equal to 19, and there is a non-deterministic loop where x gets decremented. But after the loop terminates,
Sumant, I think your voice is breaking. I think we lost Sumant's connection. Yeah, Sumant, can you connect again? I think we lost you in between.
okay, I'm connecting again. I hope it is visible now. Okay. So the previous program itself, but there is a function call here, but we do not have
Maybe
the
you
body.
can, Sumant, maybe you can start from the previous slide because I think we lost.
Okay.
Yeah.
This specification synthesis.
Yeah.
Yeah. So not only open program verification, there are other applications also like safety games, compositional verification, which all reduces to this problem of specification synthesis. Right? Intuitively, this problem of specification synthesis is you are given a set of conditions, and the conditions have uninterpreted or unknown functions. And the problem is to find some quality specification for this function. Okay, what exactly I mean by quality specification, I'll come back to it. But this function should be such that the conditions are satisfied. Okay. So to give a concrete example, say the previous program itself, but after the loop terminates, there is a function call. The function is returning some value y, and it should be the case that the value that is returned by the function should be greater than or equal to the value that x has after the loop terminates. Okay, but we do not have the body of this function. So let us represent the inductive invariant by INVX like we did earlier, and also the specification of this f by a new uninterpreted relation f, and that uninterpreted relation will have the input and output of this function as its argument. Okay, so here there is only one output y, so f of y. Okay, so now this entire program can be encoded as CHCs, something like the first two CHCs corresponds to the invariant condition that we saw earlier, and the third one, right? So here there is now new constraint on f, new constraint on y that we get from f. Okay, so now in constraint on x and f, x and y should satisfy that x is less than or equal to y. Okay, so this corresponds to the CHC encoding. So now let us look at different solutions that this system of CHC has. Okay, so the first solution is invariant maps to x is less than or equal to 19. And f is mapped to false. Now, as I mentioned earlier, right? So when do we call the mapping as a solution? It has to satisfy. It has to make each CHC valid. Okay. There is universal quantification here, which is implicit and not denoted here, but there is actually universal quantification. Okay. So now it has to make each of these implication valid. Okay, so you can see here, right? So x is less than or equal to 19 will make first two CHCs valid, and false, right? F becoming false, so the left hand side becomes false, so it vacuously makes the third CHC valid. Okay, so we call such solution vacuous. But remember that this f, right? Interpretation for f is representing the specification of the function f, right? But what does it mean to that specification to be false? So that means you are entering f, but you are not exiting f. So assert itself is not reachable. If you make assert unreachable, then assert will vacuously be satisfied, right? So you do not want such solution. Let us look at another solution now, right? So x is less than or equal to 19 still invariant, and f is y equal to 19. That is, f returns only one value 19. So this is again, take my word, this also makes all three implication valid. And it is also non-vacuous solution, right? It does not make the third CHC vacuously valid like the previous solution, but it is still not a maximal solution. By that I mean, f can return other solutions also, right? So you say f can return 20, right? So 20 is still, if x is less than or equal to 19, and y is 19 or 20, it still makes this CHC valid, right? So it is not a maximal solution. By if we do not find maximal solution, then so as I mentioned, this is a specification that will be used later on by the implementation by who implements this f, right? So they may have to consider only implementation which satisfy just y equal to 19, right? So that is not ideal solution, right? So now consider the third solution. Here x is less than or equal to 19 and y is greater than or equal to 19. So this is a non-vacuous solution, and also it is a maximal solution. Okay, by that I mean you cannot make any of these weaker by making another. You can make one of them weaker only by making another stronger. Right. So by that I mean, if you want to include one of the point in this invariant or f, you have to remove one of the point in the other relation, right? So this is the maximal relation. So the objective of the paper is that to find a technique which finds the non-vacuous and maximal solution given a system of CLCs. Okay, so this is the objective, and the key contributions that the paper makes are these. So first is we have what is known as a non-vacuous CSC solving algorithm. So it is based on a propagation algorithm that given a system of CHC, it gives a non-vacuous solution to it. The second contribution is finding maximality. Right? So that is given a solution, it will check whether that solution is a maximal solution or not. And then if it is not maximal solution, it tries to generalize that iteratively to get a weaker solution than the current one. It's our tool, which is named HornSpec, and the benchmark that is used in the paper is available in public. So if you're interested, you can go to this link and access it. So let me now give a brief overview of how our algorithm works. So first is there is this non-vacuous solving module. So the non-vacuous solving module takes as input a system of CHCs. Okay, so then it gives as output a non-vacuous solution to the system of CHCs. It does this by using a new algorithm that is mentioned, that is proposed in the paper, which works based on the propagation. So what the very high level what it does is it tries to find an initial solution for the system of CHCs, and then using what we call backward and forward propagations, it will make sure that the solution is a non-vacuous solution. Okay, and this particular module is also parameterized by the solver that it can use. So we have support for a CGUS based solver and SMT based solver. Right? So we give constraints such that the solution that is written by CGUS and SMT solver are non-vacuous solution for given input systems of CHCs. Once this non-vacuous solution is written, we do not know whether that solution is maximal or not. So there is this second module, that is maximality checker, that will check whether the solution is maximal or not. If it is maximal, that will be written, because anyway, this is returning a non-vacuous solution. If it is not maximal, it will construct a new system of CHCs, and such that a non-vacuous solution to this new system of CHC is by construction weaker than the current solution. Okay, so that way it is iteratively generalizing the solution till a maximal solution is found. Okay. So this was, as I mentioned earlier, this was implemented in a tool called HornSpec, and we compare with other solvers. So that is the non-vacuous solution. So we have our own CHC solving non-vacuous solution, and also that, as I mentioned, that is parameterized by a CGUS solver and SMT solver. So you can see here the number of maximal solutions that found. Our tool HornSpec does significantly better than if we had used the CGUS solver or an SMT solver as the non-vacuous solution. Okay, so this is the solution is the first time which can get both inductive invariant and maximal specification together. Okay, so only the solvers can find non-vacuous solutions. CVC4 and Z3, the CGUS and SMT solvers can find non-vacuous solution to a system of CGUS. It cannot guarantee maximality. Okay, so the second, then the number of iterations it took to make it maximal, right? So we have these two modules interacting with each other. So the number of iterations and how many benchmarks it took. So this pie chart is saying that we were able to solve, we were able to get a maximal solution in just one iteration to most of them. Right? So, and 2 iteration for some and 3 even fewer. Okay, so what we can conclude is the non-vacuous solutions that our module finds are almost maximal. Okay, so that is in most cases in the benchmarks, they were actually maximal. So just to conclude, I hope I have the paper, right? So the paper's title is Specification Synthesis with Constraint Horn Clauses. There are more details about the non-vacuous solving module and the maximality checking in the paper. You can refer it. So just to summarize, so the entire technique is it takes an input system of CHCs, and there is a non-vacuous solving module which will try to find a non-vacuous solution, and that solution is further extended to a maximal solution by another module which we call maximality checking. Right? So if you have any questions, you can send me an email, or perhaps if you have time now, you can ask here also.
Yeah.
So
Thanks, Suman. Started a few minutes late, so I think you took exactly 20 minutes. Thank you for keeping the time. If there are any quick questions, we can take a couple of them. But then we'll have to move on to the next stop so that our next schedule is not delayed. Are there any questions? You can unmute yourself and ask. Probably. Okay, so I have one quick question. So you mentioned that the one of the objectives of generating the maximal solutions is to sort of constrain the person who's writing that function perhaps the least, right? So you want the weakest requirement on the function.
Yes,
The
yes.
weakest requirement. So sometimes what happens is that a function gets called from multiple contexts, right? And what is weakest in one may not work in the other,
Mhm.
right? Am I making myself clear, Suman?
Yes, yes, yes. Good.
So is it just as simple as taking the two sets of constraint horn clauses from the two contexts and just solving it together, or are there? I'm just wondering, are there more subtleties to it?
Yes. So yeah. Yes. So to answer the question, so yes. So it is, if you have both constraint on clauses as well, so then it will give you a maximal solution for both constraints. So that is, yeah, it is. It's, you have to consider the other constraint on clauses also in the system of clauses. So the solution will ensure that it is maximal between both contexts.
Yeah, so in some sense, what I'm saying is that let us say there are two programs, two contexts,
Mhm.
which are in which the same function is being used,
Mhm.
and there could be some mutual dependencies, right? That maybe these two calling functions are themselves being called by somebody else.
Mhm.
So perhaps, uh, yeah, I would like to hear your thoughts on that. That how do you do? How do you solve this problem? Basically, you may have
Yes.
multiple contexts which are not completely independent, which are interdependent.
Yeah, sure, sure. Yeah, that is also possible, right? So the CHCs, as long as you can encode them as CHCs. Okay, so say for instance, if it may be a mutually recursive function and so on, right? So those things can be encoded as CHCs here. So the CHCs that we are considering is the most general form. So on the left-hand side, you can have one or more uninterpreted relations and so on, right? So it is of most general form. So as long as you can encode them as CHCs, right? So this is so we are making sure that it gives maximal solution for the given system of CFC. So it is not possible to miss those contexts also. So if
Okay.
you,
Thank you, Suman. So we'll now move to the next talk of the series. This will be given by Anand Diolekar. So Anand is a researcher at Tata Consultancy Services, and he is also a PhD student at Technical University of Munich. So Anand, if you could share your screen and start the presentation.
Thank you, sir. I have enabled screen sharing. I hope it is visible.
Yeah, we can see it.
Okay. So I'll be giving a brief overview on some encodings for checking timing properties of real-time tasks, specifically schedulability analysis. So we we are interested in checking properties of real-time tasks like deadline misses, response time, whether the task set or tasks meet response time bounds, or whether a control property is violated. So these tasks might be implementing a control algorithm or a controller, and if the tasks do not meet their deadlines, then the control application might miss some properties. So we are interested in verifying these task properties, and at the same time, given a violation of some timing properties such as deadline miss, we want to ask if it's possible to synthesize or revise the task specification by changing some task parameters. For example, suppose we are allowed to change the offsets of tasks. Can we synthesize new offsets such that the task set meets required properties? Why we are interested in SAT+SMT encoding over classical analysis is partly because most properties are reachability properties, safety properties, and the other thing is we are admitting task sets which have non-determinism through the task parameters. So whenever there is non-determinism, I'll come to that in a couple of slides. Then the closed form solutions, the existing approaches, they are pessimistic, and sometimes they are also incomplete. So with a SAT+SMT encoding, we have the advantage of precise analysis. We can pinpoint exactly where a timing property is getting violated. We have counterexamples and so on. And this precision and encoding also naturally allows us to go and synthesize new task parameters. So the work on checking properties of real-time tasks and so on has not received so much attention from the SAT+SMT encoding point of view. So this is an attempt to explore that space. So here is a example typical task model where we have a set of tasks, and to begin with, tasks are periodic. So the tasks will be activated after every period of time. We assume the tasks have an execution time interval bounded by the best case execution time (BCET) and the worst case execution time. So a task instance may terminate at any point in this interval non-deterministically. And tasks, we assume they, task instances have what is called as release jitter. So every task instance may not be available for entering that ready state as soon as the period starts, but there could be a delay which is bounded by this component called jitter. So this also causes non-determinism, and consequently a lot of task runs, different kinds of runs may occur because of this non-determinism. We assume the deadlines are implicit. That means the task instance is expected to complete execution before the period ends. And we also assume the tasks have some predefined offsets. So offset means that the first instance may be delayed by a time duration given by the offset, and henceforth after the offset the task instances, they occur periodically. We assume scheduling policies such as earliest deadline first and rate monotonic, one of them. And we assume, in particular, the scheduling is non-preemptive on a uniprocessor. So in the preemptive space, there is a lot of standard solutions for checking timing properties, but there are not many standard solutions in the non-preemptive space, given the non-determinism in the task parameters. So therefore, we chose non-preemptive. It also offers some advantages over preemptive when it comes to safety critical domains such as automotive and avionics. Non-preemptive systems have more predictability compared to preemptive systems. There's some advantages like that. So we'll also assume that the property we're interested in is to check if tasks meet their, miss their deadlines. So if they miss deadlines, we are interested in going and correcting or revising the task specification. So here is an example. The table gives us a task specification. We have 3 tasks here with offsets set to 0. There is some amount of jitter in each task. And the periods are 10, 30, and 60. And this is the execution time budget. It's a very simple illustration just to showcase what's happening. So here is a task run. And note there can be many possible task runs because of jitter and execution time variation and so on. But here is an example run where the second instance of task 1 misses deadline, because while it is released here, it is ready to run. It could not be executed because the processor was serving task number 3. And we would like to figure out whether such deadline misses occur given this task specification. So what we do is we first of all bound the number of jobs. So we assume there is an analysis horizon, and tasks are the task instances are spawned, jobs are spawned up to this analysis horizon. The analysis horizon could be, for example, hyper period of the tasks. That means the LCM of the periods, or any other value. So we have an array which is used to store a task run. So this array will store things like start time and the end time and the release time of task instances or jobs. Now, for each job, we are going to guess a location in this array. Since we do not know what exactly could be the possible set of positions for each job, we are just going to guess it. And we are also going to guess the release start and end times of the jobs. So there is no explicit scheduler in this encoding. We are going to construct a formula which encodes all possible runs of the task set. And we'll conjunct this formula with the property of interest, in this case, deadline miss. And if there is a violation, we'll get the run in this array showing the deadline miss. Now, these guesses on the location and the times, that is release, start, and end of jobs, they need to be constrained. So we start picking the basic constraints coming out from the task specification. So for example, the release time of every task instance is bounded by the jitter. So the task instances are released, offset plus the ith instance into the period, and then up to the jitter value. So the release could be any value, for each instance in this interval. And obviously, a job can start execution only after it is released. And the execution time is bounded by the best and worst case execution times. And since it's a uniprocessor execution, where one job follows the other, we get this constraint on the array saying that the next job can start only after the previous has finished. Now, next, we need to encode the scheduling constraints to make sure that the task run is as per the scheduling policy. So, for example, under earliest deadline first, we know that jobs are going to be sorted on their deadlines. So consider two locations L and L prime, where L is less than L prime. So if a job has been scheduled before another job, then it must be the case that the deadline is earlier, or they were not, these two jobs were not contending. In which case we know that the job at L, it started before the other guy, the other job could be even released. So this is the scheduling constraint, and it needs to be applied on every pair LL prime that could contend. So the constraints, the scheduling constraints typically can be quadratic in the number of jobs or the size of the array. And similarly, under rate monotonic, where there is a priority assigned to the tasks, a static priority, the job at L prime will succeed the job at L if its priority is lower, or of course they do not contend with each other. Now, one more constraint is required called work conservation, and work conservation means that when there is a job or task instance that is ready to run, the processor cannot be left idle. It has to immediately service the job that is waiting. So since we are guessing the start times and so on of jobs, we need to now encode work conservation constraints. So I'll not get into the detail, but this figure, sort of just glance through this. So consider this job here, the lower one, and you can see the red lines indicate gaps. That is, the processor is idle and it should not be idling. So for example, one necessary condition to eliminate this idling is that if there is a waiting time, if a job waits after release, it is ready but it is not yet scheduled, then it must be that it should be scheduled immediately upon the termination of the previous job. So this closes the second red line, this idle gap here. And now to close this idle gap is a bit more tricky. So basically, what we need to do is, every time there is a idle gap between two consecutive jobs, which is encoded by this constraint here on the LHS of the implication, then we need to ensure that jobs following the idle gap, they cannot be released before the idle gap. Now this has to be checked sort of with a existential quantifier, and that can be eliminated because we have a finite number of jobs. So it's possible to impose certain nice constraints and an ordering, and that is what this cutoff array, pre-sorted cutoff array, is doing. So it makes sure that this idle gap is closed. So again, we need constraints which are kind of quadratic in the number of jobs here. Now, to encode the deadline miss, we simply add a constraint asking if it is the case that a job ends after its deadline. So if this is true, the set of constraints that we have so far collected, if they are satisfiable, then we get a counterexample demonstrating a deadline violation. And the encoding that we have is, we have a template, C program template, in which we fill up the task specification parameters. And this C program is given to CBMC with Minisat as the backend. And we experimented with this setup. This works for small task sets and a small analysis horizon, but overall the scalability is poor. That's because there is huge amount of guessing in terms of the location of the job and other non-deterministic parameters. And especially the analysis is very sensitive to the number of jobs, so it doesn't scale beyond typically 100 jobs or so. So still, whatever we can do with this is something more interesting. So now suppose I get a counterexample showing that here is a deadline miss. Now I want to go and revise this task set, and let us say I'm allowed to change a task parameter, the offset. And if I change the offsets now, can I make the task set schedulable? So the counterexamples, this was the counterexample we had obtained. Let us look at it closely. And the observation is that, let's pick up task number 3. The observation is that if I change the offset of task 3 from 0 to 10, I pick any value between 0 and 10, this interval 0 and 10, then the result is that this deadline miss cannot be avoided, and the same counterexample sequence, the job sequence, is still maintained. So, but if I choose a value just outside this interval, let us say value 11, the new offset for task 3 is 11, then I get a, then the new task set is now schedulable. So now the point is to extract out these intervals, which we call as deadline miss preserving intervals. So we want to extract these intervals from the counterexample, and we want to remove this these intervals from the space of offsets of the task set. Anand, so the way to do is this.
Anand, yeah, if you could try to start wrapping down. I mean, we have one more.
Yeah. Okay, sure. Yeah, I'll take another minute. Yeah. So the way to do it is we have a we use an optimizing SMT solver where we have all the schedulability constraints and we have the deadline miss here, and we say that this particular sequence must be retained. Now go and maximize the offset. So for O1 I may obtain O1 bar, and O2 I may obtain O2 bar, and so on. Now it can be shown that these offsets can be composed, and the composition is sound in the sense that any combination of values of offsets in this region is still going to give me a deadline miss. So given this kind of analysis, now we are in a position to synthesize the offsets such that we get a schedulable task set. So we start with the initial task specification, and we ask the model checker if it is schedulable. If not, we go and mine these intervals, compose them to get hyperboxes, and we ask the SMT solver to give a point outside this hyperbox, and this loop continues till we get a new value of offsets such that the task set is schedulable, or we run out of the offset space, in which case the task set is indeed unschedulable. So some experimental results, we chose the task sets randomly, up to 50 jobs and some 5 minutes of analysis time. So the schedulable task sets, we could refine with up to 2 refinement steps, and we could obtain a new task set which differs only in the offsets and is now schedulable. And those which were unschedulable took like about 6 refinements. But the task set size and number of jobs we could analyze still remains low. So this was published a couple of years back, and what we are doing is work in progress. We are now trying out a new SMT encoding, doing away the CBMC SAT encoding, and we are also trying to target multi-core analysis where we'll support more than one processor. And the basic idea to try achieving scalability is to construct a DAG of jobs where the vertices are jobs, and there is an edge between two vertices if and only if we know that statically that job will be scheduled before the other job. So this is possible. This DAG construction is possible depending on the scheduling policy. And this DAG is basically going to give us a partial order over the job sequences, and thereby it prunes the total number of sequences to be analyzed. With this, we are able to achieve a order of magnitude scale over the earlier encoding. But of course, this also does not scale to more than 6 or 8 processors. So task sizes up to 10, 12, and some 4 or 6 processors can be handled with this. Okay. So I hope this gave an idea into what we are doing in the space of analysis of real-time task properties using SAT and SMT encoding. There are also several open problems in this space, and we are hoping to look into it as we go ahead. Thank you all. Any questions? You could feel free to ping at this point. Thank you.
Yeah, thanks, Anand. So yeah, it turns out that I think 2 of the speakers of the next session have not yet sent me a confirmation yet. So we may be able to just have some discussion in the remaining 5 minutes and have the third talk, which was scheduled in this session, in the next session. Is that fine with you, Divyesh?
Yeah, I think we can do that.
Because in any case, there are 5 minutes left before 4. And it looks like 2 of the 3 speakers in the next session have not yet confirmed. I don't know if they'll just join Zoom at the last minute, but yeah, so I suggest that we have some discussion maybe for both the current talk and the previous talk in the next 5 minutes, and then we have Divyesh's talk followed by Akshay's talk in the next session. Okay, if there are any questions for Anand? I'm not checking the Discord server. Okay, so while I check the Discord server, if nobody has any questions, maybe I have some slightly generic questions for Anand. You know, in one of your initial slides, you said that if you can go back, I think maybe to first or second slide. Yeah, you said why SMT solvers. Yeah, right. So you said why SMT solvers, and of course this is a SAT+SMT winter school. So this is, of course, everybody here knows the importance of SAT+SMT. But I mean, could you speak a little bit more on maybe your experience with maybe MILP solvers, maybe because yesterday we heard a lot about how MILP solvers outperformed SMT solvers for neural network verification. So if you have tried MILP solvers in this case, could you speak something about your experience over there?
I'm sorry, I haven't yet been able to do a MILP encoding.
Oh, I see, I see. Okay.
I am interested because most people are either using classical closed form solutions for checking real-time tasks,
Mhm.
or they are deviating towards MILP. Very few people are trying out model checkers and SMT solvers to check properties in this space.
Mm.
The general comment I've heard is that scalability is a big concern, and beyond a handful of tasks, it's difficult to scale. So with MILP, the thing is to handle this or encode this non-determinism and various possible sequences of jobs. So the encoding is a bit to be worked out, uh, but so I still do not have any uh, experience with MLP.
Okay, okay, okay. That's yeah, that's good. I mean, yesterday I think you attended yesterday's talk, right? So Gagandeep made a strong
Yes.
case for MILP solvers, at least in neural network verification.
Yeah,
And
in fact, he said he did not get very good results with SMT solvers,
mm-hmm.
and I think he also has promised to speak why SMT did not do a good job. But I guess in the flow of time, he could not cover it.
Yeah, I mean, he mentioned briefly that it's the structure of the constraints that so repeated affine constraints plus these constraints from the activation functions. So it's a large number of constraints of the same type, but there's an affine constraint followed by something. So he mentioned briefly about that. I do not know whether that explains the performance inefficiency. Uh, but yeah, I think it is it might be an interesting idea to also try out the latest. But you're saying that in the literature people have already tried this out, MILP solvers for solving problems.
Yes, people have tried MILP encoding. For example, there are a couple of papers by Professor Marco Natale,
Mhm, mhm.
and he has been using MILP encoding with good effect.
But is he able to solve the kinds of problems you're trying to solve?
Yes, in fact, he's able to solve slightly more involved problems. Uh,
Mm-hmm.
he's able to check, for example, if uh, weakly hard schedulability properties are violated by task sets. So that is, instead of one deadline miss, is in any window of say size W, is more than W um, is more than W deadline misses. Is it occurring at any point? So that is in fact slightly more involved than our setting. Is able to solve such kind of things with MILP.
Okay. If there are any other questions, you can unmute yourself. Uh, just quickly check the Discord thing.
Okay, thank you. I'll stop sharing the screen.
Uh, yeah, yeah. Uh, just 1 second. I don't think there are further questions on Discord as well. Okay, so then we'll take a short break of 15 minutes and we'll reconvene at 4:15 Indian time. And then we will have the first talk by Divyesh Unadkar. Uh, then I mean, if the other two speakers show up well and good, otherwise we'll also have a talk by Akshay. So at least 2 talks we're going to have in the next session. Let us see whether, oh, Himanshu has shown up. Okay, so we'll probably have 3 talks in the next session. Okay, great. So we'll see you in 15 minutes. Himanshu, can you please unmute yourself?
Yes, I'm here. Hello, am I audible?
Yes, you are.
Okay.
Can you let me make you a co-host so that you can share your screen? Yeah, can you quickly share your screen so that we can see if it's working?
Sure. Is it visible?
Yes.
Okay, all right.
So, we slightly ran over time in the previous sessions. So the next session, the first talk will be the talk that was originally scheduled as the last talk of the previous session. Then we'll have your talk, then we will have Akshay's talk.
Okay, no problem.
But I think the last speaker is not speaking.
So like we'd have a talk first, then it would be mine, right?
Yes.
Okay, sure.
Okay, you can unshare your screen.
Hello, Supriti, can you hear me?
Hi, Akshay. Yeah, we can hear you.
Yeah, so I'd also like to test my thing.
Yeah.
By the way,
Great.
you know that you are currently on live stream still, right?
Yeah, we'll edit these out.
Wonderful. So let me just share my screen to be sure that this works. At least my mic works, which is an improvement from yesterday. Let me quickly try this out. Just hold on.
I'll have to make you a co-host.
Oh, is it? Could you please do that? Yeah. Yeah. I'm going to just hold on. I'm not able to. Yeah. Okay. So I'm just sharing my screen. Is everyone able to see my screen?
Yeah, we can see.
So you're able to see the talk that is running right now?
Great.
Yeah, 1 second. Let me just do the, so is this still visible?
Yes.
Okay, and when I do, this is fine?
Yes.
Okay, great. I think that's all I need to, yeah, so there is one place where there's a video where it's going to be slow, but otherwise I think the rest should be fine. Okay, all right, thanks. I will stop share right now.
Sure. Divyesh, are you there?
Yes, Subhadeep.
Yeah, maybe you can start sharing your screen. We'll start in a minute.
This will start. Okay. Just a sec. Okay. Do I
Yeah.
need to turn the camera on also? No, that is fine, right?
It's up to you. Yeah.
Okay, it's okay.
So yeah, you can see your screen. Okay, so welcome back after the short break. So we'll continue with our short talks. So I think we will have 3 short talks this session. And after that will be the invited tutorial from 5:30 p.m. Indian time by Professor Marayan Hule. So the first talk in this session will be by Divyesh Unadkar. He's a researcher at Tata Consultancy Services, and he's also a PhD student at IIT Bombay. So Divyesh, floor is yours.
Thank you, Professor Sukrati, for the kind introduction. So
Please
this is
keep to 20 minutes because
certainly,
yeah.
certainly. Yeah, so this is joint work with Professor Supratik and Professor Ashutosh, and this is published at CAV 2021. So software is being increasingly used in day-to-day appliances and devices. In such software, arrays of parametric size are used to store and process data. In such implementations, the size is instantiated during deployment based on the make and model of the appliance. Various libraries also use arrays of parametric size, and such libraries are commonly used across various applications. It becomes important to verify properties of such software when they are safety critical or business critical. So let's take a concrete example. Here the function foo updates array A of parametric size n, possibly within nested loops or branch conditions. We denote such programs as pn, and here the pre and post conditions are denoted as phi n and psi n. These can be quantified or quantifier free and may have non-linear terms. Given such a precondition, we want to establish that the post condition psi n holds when program pn terminates for all possible values of n greater than 0. Previously, we have designed this technique called full program induction to verify such hold triples. The idea here is to induct over the entire program via the program parameter n instead of inducting over the individual loops in the program. In the base case, we check that the hold triple holds for small values of n, say 1. If the base case fails, we know that the property can be violated. Once the base case succeeds, in the induction hypothesis, we assume that the hold triple phi n, p n, psi n holds for the parameter n minus 1. And for the inductive step, the technique tries to relate pn minus 1 and pn. So it decomposes pn into two programs, pn minus 1 and delta pn. It calls delta pn as the difference program. It also decomposes the given precondition into phi n minus 1 and delta phi n, where the delta phi n is available to the difference program when it is not perturbed by pn minus 1. So as you can already see, the hold triple on pn minus 1 is available for free from the induction hypothesis. Hence, in the induction step, we only need to establish the hold triple on the difference program. Note that the entire reasoning was on the entire program and not on individual loops in the program. Whenever the difference program turns out to be loop free, this technique works, it simplifies verification. And it's possible for several programs that the difference program is indeed loop free. However, for many cases, computing the difference program is very, very challenging. So let me take one such concrete example. Here, the program pn has two sequentially composed loops. In the first loop, it computes the value of variable x and array a. The value of x depends on its value in the previous iteration, as well as on the expression n squared. and the value of array B depends on the value of X computed in the previous loop, as well as on the loop counter. So there are all sorts of dependencies here. If we were to apply full program induction, it would have to decompose Pn into two programs, Pn-1 and delta Pn. In Pn-1, all occurrences of n are replaced with n-1, including the loop guards as well as the expressions within the loop body. Hence, the values of variables in Pn-1 may be different from their values in Pn. And what the difference program does is, it tries to rectify the values of such variables and arrays, possibly within loops. It also accounts for the iterations that were missed in Pn-1 due to the change in the guard. These are shown in colored boxes with solid lines. As you can already see, constructing such a difference program may be quite challenging. In several cases, it may happen that the difference program again has loops. For example, in this case, it has two loops. And so we are unable to simplify verification. And here, verifying Pn may be as hard as verifying the difference program. So your inductive step may be as hard as verifying the property directly. Recursively, if we try to prove the inductive step using full program induction, it may again turn out to be as hard. And even when there are no nested loops, one may have to apply the technique recursively. Again, this full program induction technique did not support nested loops and branch conditions, where the value was dependent on n. So how can we overcome these limitations was the question in our mind. And our work at CAV overcomes these difficulties. So the idea is, rather than putting effort in computing a very complex difference program, we want to use a very simple difference program, which is just the peel iterations of the loops in your given program Pn. We represent that by peel Pn here. And we use a slightly modified version of Pn, which is Qn-1. This is different from Pn-1. And Qn-1 is such that we can use the peel iterations of all the loops as our difference program. So let me take a concrete example to show you how Qn-1 and the difference program look like. So again, this is the example that we have just seen, where computing the difference program is quite challenging. So we'll not compute the difference program in full program induction style. Instead, we'll use just the peel iterations of the loops as our difference program. And this is how the program Qn-1 is going to look like. And it turns out that there is a very simple way of computing Qn-1 and peel Pn. So what we do is we peel each loop, we peel the last iteration from each loop in the program. Then we identify the uses of variables that are defined in the peel. So for example, X used in the second loop was defined in the peel. We substitute these uses with that was used to define those variables in the peel. So here X is substituted with X plus n squared. And now the peel is independent of subsequent uses. Right? So this is how Qn-1 and peel Pn are computed. And this is an algorithmic process. And it also supports nested loops. So here I have shown an example of nested loop. So for example, I goes from 0 to n and j goes from 0 to n. This is a very simple case of a nested loop. What we do is we view the inner loop as being unrolled n times. And then we peel this loop. So here, the last iteration of this loop is separated, and the last iteration of the inner loop is also missed for the previous n-1 iterations. So that also is it gets peeled. So essentially, in the peel, we get a sequential composition of two non-nested loops. Right now, to propagate such a peel with loops, one may require to compute closed forms, or one may require to summarize such loops. So there are several guarantees that our method offers. So one is where whenever for a class of programs where upper bound expressions of loops are linear in n and loop counters of outer loops, it guarantees that the nesting depth in the peel Pn program is strictly less than the nesting depth in the given program Pn. With each application, this is guaranteed. And this decomposition of Pn into Qn-1 and peel Pn, it preserves the semantics. So these are the guarantees that come with this technique. Now, since Qn-1 is different from, it can be different from Pn-1, the post condition also can be different. And we'll just shortly see how this post condition is computed. We have also generalized the decomposition of the given precondition phi n into phi prime n minus 1 and delta phi prime n. Let us see this decomposition with an example first. So consider the precondition phi n as for all I in 0 to n, ai is n. Right? The full program induction technique could not decompose this because it cannot happen that at ith index the value is n as well as n minus 1. So instead of substituting n with n minus 1 across the entire formula, what we said is substitute n with n minus 1 only in the guard expressions of quantified formulas. And that is how we represent phi prime n minus 1. So now computing the difference is simple for this case. It's a of n minus 1 is n. And the side condition is retained, which says that qn minus 1 must not modify variables in the difference precondition computed. Once we have computed this difference, we now proceed to computing the post condition of qn minus 1. This is the most interesting part of the work, and it is the main contribution. To compute the post condition of qn minus 1, we infer relations between corresponding variables in pn minus 1 and qn minus 1. We call them as difference invariants. Once such difference invariants are obtained, computing the post condition is simple. We can directly use the post condition from the induction hypothesis, and using a quantifier elimination, we get the post condition. We use a simple guess and check procedure to obtain such difference invariants. We use very simple templates as shown here. And we have observed that computing difference invariants is much simpler in most cases as compared to computing loop invariants. So again, let me take a concrete example to show you how these difference invariants look like. So consider this whole triple phi n p n psi n, which has two sequentially composed loops. The first loop modifies x, second loop modifies b. And we have computed this program qn minus 1 using the procedure that I have just outlined. And we want to relate the variables computed here with the variables in program with parameter n minus 1. So pn minus 1 is obtained by substituting all occurrences of n with n minus 1. And the difference invariants are shown here. So for the precondition, it says that the value at ith index in a prime minus a is 1. So the difference in values here is just 1. Similarly, since x depends on the value of a, the differences in values of x during each iteration turns out to be 1. And since there are n minus 1 iterations, this difference turns out to be n minus 1. And now the difference invariant for relating b and b prime is as shown here. It depends on x, and in each iteration there is a contribution of n. So it turns out to be 2n minus 1. Once we have computed these difference invariants, we use this simple formula to get the post condition of qn minus 1. Note that the post condition here for qn minus 1 is different from the post condition of pn minus 1, right? And once this post condition is obtained, we can now proceed to the inductive step that uses this post condition as a part of its precondition. It may happen that we may not be able to prove the inductive step directly. That is, assuming psi prime n minus 1 composed with the difference precondition, we may not be able to prove the post condition psi n using peel pn. In such cases, we use Dijkstra's weakest precondition to compute a strengthening of the precondition denoted as chi prime n minus 1 here. Previously, we were able to use the same predicate. So for example, pre n minus 1, we were able to use the same pre with a different parameterization to strengthen the post condition as well, because whatever holds after n minus 1 iterations must also hold after n iterations in the inductive process. But here, since we are using a slightly different program, that is qn minus 1, we must use a different predicate to strengthen the post condition. And these it so happens that this chi prime and chi are related via the difference invariants. And using a simple quantifier elimination, when the difference invariants are linear equalities, we can obtain a predicate that strengthens the post condition as well. Yeah, so our technique is sound. That is, whenever the base case holds and the strengthenings are related via the difference invariants and the inductive step succeeds, then we conclude that the parametric Hoare triple holds for all positive values of n. We have implemented these ideas in a prototype tool called Diffie, and we have compared it against various other tools such as Vajra that implements full program induction, Variabs that implements various strategies in its portfolio, such as loop shrinking and pruning, as well as VIAP that relies on solver techniques. And we have compared their performance on a large benchmark suite of more than 300 programs from SVComp as well as from other suites. These are divided into various categories depending on the complexity of the operation, such as C1 has standard programs, C2 has programs with branch conditions affected by N, and C3 has programs with nested loops. And as can be already seen here, Diffie outperforms all the other tools which have already won SVComp in the past. In terms of time, our tool is significantly faster as compared to the other tools. On safe programs. On unsafe programs, we report a violation only when the base case check fails. So this work is published at CAV 2021. Do look up our paper. Our tool Diffie has received the highest artifact badge. It is functional, reusable, and it's publicly available at the link here. You can scan the QR or you can refer to the link here. So to conclude, presented a novel property-driven and efficient verification technique. It performs very simple transformations that enable full program induction. Computing difference invariants in an inductive framework gives you, a different way of proving programs as compared to just using loop invariants. And in our case, the difference invariants that we computed turned out to be much simpler as compared to loop invariants. We plan to extend this work beyond whatever the programs that are currently supported, as well as we plan to enhance the way in which you compute difference invariants. Thank you for your time, and thank you for giving me this opportunity to present. I'll be happy to take on questions if any.
Thank you, Divyesh. If there are any questions, please ask them. You can unmute yourself and ask.
Akshay has a question. He has raised a hand.
Yeah, please go ahead.
Okay. Yeah. Can I go ahead? Yeah.
Yeah.
Can you hear me?
We can hear you.
Yes,
Yeah.
yes, Akshay, we can hear you.
Yeah. Hi, Divyesh. Yeah. Thanks for the nice talk. I had a couple of questions. One is, so you said that this works with arbitrary nesting of loops also, right? In your technique.
Yes.
But so when you don't have, that is when you don't have nested loops,
yeah.
How does this, will this differ in any way from the earlier approach? Is there a benefit even in the case without nested loops?
That is what I tried to highlight.
Yeah, I missed something there. Yeah, could you just, so how does it differ in the case where there are, yeah, exactly.
Right. So previously we had to compute a difference program, right,
Correct.
which is shown here as delta Pn.
Mm-hmm.
And it had to rectify values of variables such as x and I, as because in the induction hypothesis you assume that Pn minus 1 has already executed, and you are going to assume the post condition after Pn minus 1.
Sure.
So this rectification now is not required here. I can just use the peeled iterations of all the loops in the program as my difference program.
I see.
Right. So now, yeah.
Okay, go ahead.
So my technique does not need to automatically synthesize such complicated expressions within loops. So this loop I don't need to synthesize. I just use these peeled iterations. However, some amount of complexity gets translated into computing the difference invariants.
Correct.
So previously, I did not have to compute difference invariants because the post condition of the induction hypothesis was directly available for free.
Right.
So here, this psi n minus 1 is obtained from psi n just by substituting n with n minus 1. Right. I cannot use that directly. I have to compute some difference invariants that relates psi n minus 1 with psi prime n minus 1 over here.
Right. So, and if I understand correctly, the difference invariant is really what is the difference between the variables, an invariant on the difference in the variables that you are defining, right?
Exactly.
Right. So like
yes.
Here, yeah, between this Q and P. From
yes.
Here, right. So that leads me to the other question. So the extra complexity seems to be in this existential quantification that you're doing. Is that right?
Yes, some amount of complexity is in the existential quantification.
So is that what you see, for instance, when you're implementing, like how much of it is because of this existential quantification?
So for example, right now, I only support such cases where this difference invariants, they are equalities, In such cases, this existential quantification turns out to be quantifier elimination. Otherwise,
Right.
this is an abduction
Right.
kind
But
of
then,
a thing that one has to do.
correct. Right. So then how do you, like all the benchmarks happen to be in this setting? Is it that the different things? So that's a little bit surprising. Is it surprising?
Well, as you have already seen, there are several examples where, several state-of-the-art tools and techniques do not work. Even my previous work, which is inductive reasoning based, will also struggle because the difference program is very complicated. But this simple procedure works.
Oh, so it's
and verification, given that verification is in general undecidable, no technique will be able to do everything.
No, of course. No, my question was, where does the bottleneck hit? Like, I mean, are you able to, so when you say that you have only equality as difference constraints, that must constrain the type of programs, right? So in the benchmarks, are there other programs also?
That is for the prototype implementation. In general, the difference invariance can be anything. But in those cases,
the theory I understand.
Strengthening the post condition may be slightly difficult because you will have to compute this chi. And there you may not be, the quantifier elimination may not suffice. You will have to do abduction. And then again, the abduction procedure will become, in some sense, a bottleneck.
Okay, thanks. Yeah.
Thanks.
We'll take out. Yeah.
Any other questions?
Okay, if not, thank you, Divyesh. And then we'll move to the next talk, which is by Himanshu Shivran. Himanshu, if you could share your screen.
Sure. Am I audible?
Yes, you're audible.
Okay.
So Himanshu graduated with a BTech in Computer Science from IIT Bombay earlier this year. And he is currently working at VMware in cybersecurity. He is very interested in using SMT solvers to reverse and crack security related stuff. And I think he's also part of this Capture the Flag community where he has seen extensive use of SMT solvers. So Himanshu, the floor is yours.
Thank you, Supratik sir. And so I'll start presenting. So hello everyone. So I'll be
keep to 20 minutes. Okay.
Okay.
Because,
I'll try to. I'll be talking about the state and seed recovery of random number generators. So this was a little project by me and my batchmates, Sahil Jain, Yash Parmar, and Lakshya Kumar. So let's quickly talk about pseudo random number generators. We all know that computers are deterministic, and in a lot of places we don't like determinism. That is, we want our deterministic machines to produce random sequences because we have a lot of applications which we would not like to be deterministic. So we fool ourselves with seemingly random sequences of numbers which behave random statistically, but are they truly random is highly debatable. So how a typical pseudo random number generator works is that we have a finite state and we have some operation which modifies this state, and each operation generates an output which is seemingly random, and depending on the use case it could be a sequence of bits, bytes, words, etc. So what could be the consequences? Anyone who considers arithmetical methods of producing random digits is of course in a state of sin, as says John von Neumann. So who's there to save us? RNGesus. So what is RNGesus? We created a tool which cracks these random number generators and tries to predict the future outputs based on some outputs from those generated random numbers. So why do we need such a tool? Because to demonstrate that at a lot of places, pseudo random number generators are used which are not cryptographically secure, and whose place cryptographically secure random number generator should be used. So for example, online casino, casinos need a lot of random numbers. They need a random number to generate the lottery tickets. They need random number to generate the draws. They need random numbers to give out who's the winner. A lot of places you would see there are password generators which use random number to generate random passwords, and we don't know like if a given implementation of password generator is actually using secure random number generators. It could be unique file sharing IDs, it could be some URL shortener, and unfortunately we see a lot of cryptographic places where we expect nonces which are not generated by cryptographically secure random number generator. So real world examples would be, it was a case in 2010, a guy figured out the random number generation in a state lottery who was initializing their state properly, but they were using a weak RNG, and it resulted in him winning 16.5 millions and 20,000 per hour in CSGO skins. So it is a very popular game, and a lot of customizations and skins go into it. So people have some games where they organize a jackpot and a random number is used to select who of a current pool is gonna win. So if you tune everything perfectly, you can determine yourself be the winner each time, and you would be earning 20,000 per hour. And a guy reverse engineered the slot machine and figure out the internal random number generation algorithm and found out that okay, I can break a slot machines which is expected to lose money over time, but he won like $21,000 in 2 days. And even the implementations such in Android, so Java secure random generation was not actually secure, which led to Bitcoin wallets to be generated through Android to be highly vulnerable, and it was patched later in 2013. So what are we cracking? So our primary interest was the Merchant Twister. Why exactly? Because it is used. It is the most used general purpose PRNG and has very fantastic statistical properties. It is used in almost everywhere: Python, PHP, C++, all the programming languages and all the places you can think of. If you grab all the instances of random number generators in the world and pick out one, it would definitely be Merchant Twister. Why is it called Merchant Twister? Because it uses a state of 624 integers of 32 bits, and the repetition sequence is very large, that is 2 raised power 19937 minus 1, which is a Merchant prime. That's why it's called the Merchant Twister. And there are other influential random number generators which are used typically. Linear congruential generator is one, which is very widely used and very simple to implement and performs very fast, as it is simply a multiplication and addition operation modulo some number. Then Knuth figured out that okay, this is not good enough for statistical property. We can just output some bits out of this random number generator, and it has better statistical properties and better reversing properties in the sense that we need it won't be much more guessable. And in hardware levels, we have several LSFR combinations, which is simply linear feedback shift register, and they are combined in multiple ways, and using those combinations we generate an output. So let's talk about the Merchant Twister. So it's basically a linear recurrence of 624 length, you can say, and the 624 plus ith number is dependent on ith number and I plus 1th number and I plus 397th number. So a single bit of ith number is used, 31 bits of I plus 1th is used, and all of 397 plus ith is used. And how it is typically implemented is that there would be an array of 624 32-bit words and an index which would keep a track of where the things, where we are which number exactly are we pointing in the array. And we will keep on outputting from that array until we reach the end of the array. We would reshuffle it and recompute this whole recurrence. So usually it is implemented by a twist operation, and this twist operation defines like what would be the next 624 word array. And as this array itself is not suitable enough to produce an output, it is typically gone through tamper operation, which essentially does is reshuffles the bits so that they are more suitable for statistical properties. But this whole operation is bijective. So given an output, the initial state can be determined easily and effectively using bitwise operations. And this is one such bitwise operation which makes one ponder that, okay, SMT solver would be good in determining these relations. Otherwise, we would have to look at each and individual bit by our hand. And the seed is initialized to create this 624 state array. And the seed initialization is fairly easy. So we select a single 32-bit word and we generate words out of it based on the last word we saw. So this is how we create a 624-bit, 624 length array. So what we do is we XOR and shift it and multiply with the number. And as you can see that this number specifically is the seed. And the relation from word I and word ith minus 1 is bijective. So if we know a single word, we can know all the words in that array. So this further leads us to ponder that, okay, this might be very specific case where SMT solvers would be able to figure out the relationship between different bits and words inside that array. And what's funny is that the whole initialization of almost 20,000 bits is done using 32 bits. So what we do is we essentially create a constraint, a symbolic constraint out of each variable. So first, the output is produced by the internal state by tampering it. So we create a symbolical expression which essentially states that this is the resulting operation. And if we expand it, this is the output based output expression based on what input state was used. So if we give this to SMT solver, it is fairly easy for it to determine that these were the input to generate this particular output matching a number. And this is how we would do in a typical SMT case, that we would create a bit vector of 32 bits. We say that this is the expression for a tampering, and given this number, what was the original number whose tampering resulted in this number. And also we would, since after each 624 output, this is twisted, we need to untwist it to find out that, okay, what was the original array which resulted into this 624-bit array, 624 output array. And as we would do the computation in a simple number, we would define such computation for symbolic variables. And to simply get the seed out of a specific sequence of outputs, we would create a sequence of symbolic variables, and we would initialize the way it is initialized in a normal random number generator. We would give it the outputs and ask for it to solve for what exact seed could have resulted in these outputs. So typically we would expect that 624 outputs would be needed, since we have 624 variable state, and each of them is used to generate an separate output. But turns out that this seed initialization was not so good, and we don't need 624 outputs. We actually need 4. And it's funny to know that a 32-bit seed can be determined easily using 128 bits of output in about 200 seconds. So this was a very fine result that we didn't expect. And someone might argue, okay, Himanshu, that no one uses 32-bit random numbers. So what we typically use is we either use a random number from 0 to 1, or what we do is we take its modulo sum operation and so on. But this makes a perfect case for using SMT solvers to determine the case. For example, if we take a normal random number generated from 0 to 1, what internal implementations of random number generator do is they generate two 32-bit outputs, extract out 26 and 27 bits from each of them, and since floating double precision floating point integers use 53 bits to determine the number and 10 bits to determine the exponent, if we fix the exponent, then we have 53 bit of uniformly random generated numbers we can give out. This is how it is usually given out to generate an output. So we can just create these constraints and we can simulate exactly how it would be done. And that's what we did. But we found out that this requires 624 outputs to determine the whole initial state. And it takes less than 60 seconds to know. And SMT solvers find it very good to find a path which would lead us to this specific state. So it sounds all easy, but there are usually some hidden requirements which we need to figure out. First of all, what encoding of the output are we looking at? So we need to determine how was the random number used to find out the given output. So if we know that how is given output is generated, and if we can decode to find out the internal representation like we did for random floating point from 0 to 1, we can find it. And if there are any hidden transformations on the generated outputs. And the most challenging thing which we found out is that continuity of the output number generated. So we don't have information on what typical internal state of RNGs are used, and typically in a lot of applications, this would be consumed by a lot of clients, you can say, and each one would get a very different output. So, but if we figure out these conditions as we saw in those hacks, because some random number generated are client based and client can see that what exact sequence of operations are used, we can figure out the random numbers. So this is the tool we created, and these are the other references on Muss and Twister, you can see. So thank you. And also, like, this leads us to other interesting approaches of doing the same. So after we did this, we saw specific tracking of RNGs using similar 128-bit outputs using machine learning models based on LTSMs. So thank you. I think that's the end of my talk.
Thanks, Himanshu. Very interesting talk. If there are any questions, please ask them. We have a minute or two. So, Himanshu, which SMT solver did you use? I mean, was there?
Oh, right. I forgot to mention, we used Z3 on Python.
Okay. So, and what kind of theories did you use? Just bit vector theory or?
Just bit vector.
Okay. So, yeah, I'm you know, the results look very interesting, and I'm just wondering, whether there was something that made the problem so easy for the SMT solver while it is being used in the state of the art.
Yes. That's the whole thing. So if we take a look at the seed initialization, so it is very straightforward. It uses a single 32-bit seed and use a bisective map to compute this. But what people nowadays do in a lot of implementation, you won't find this seed initialization, and it was updated to a better seed initialization, which is based on a whole array of seeds, and it is highly nonlinear, you can say. So I have also included that. Oh, sorry. So this is the seed initialization you would see in most of the cases, but in some cases, for example, NumPy random number generation. So NumPy uses that seed initialization, which I mentioned. So this one is not easy to crack given 4 outputs, because it depends.
So an SMT solver finds it hard to crack.
Yes. So we can crack it, but we would need the whole 624 output to find the seed. I also implemented this one, and this takes also around 5 minutes, but we need much more outputs otherwise. Like we would need complete like 20,000 bits instead of 128 bits, which is quite some difference.
Okay, very interesting. So is VMware using such stuff?
Not yet.
Okay. Are there any other questions?
Yeah, I had a quick question.
Sure.
Go ahead.
Yeah, so you, first of all, a wonderful talk and a really nice punchline. But you said at the end that recent work using LFTMs is able to do the similar kind of reasoning or whatever, reach the same thing. How do you compare your performance with respect to that?
Our performance is, first of all, exact accurate. So what these LTSM works do is they find out the bits, but the you can say, what do we call that? The sequence of bits is not determined. So they would be shuffled, but the bits would be correct.
I see.
So it would be like 95% 95% bits would be correct. And if we actually see the correct outputs, it would be 30-40% of the outputs would be predicted correctly, because we don't know the order of the bits. So they are their own things, that they are instantaneous because they determine the output instantaneously once the model is trained. But this take around like 2-3 minutes to find out what was the exact state. So they have their own cons and pros, but I think this one is better.
Great, thanks. Yeah, good.
Okay, thank you then.
Thank you. Is there another question? No. Okay. Thank you, Himanshu. Yeah, maybe you can unshare your screen and then we'll proceed with the next talk.
Sure.
Will be the last talk of this short talk series. So the final talk will be by S. Akshay. He is a faculty member in the Department of Computer Science and Engineering at IIT Bombay. He's done a lot of very interesting work in various areas of formal methods, logic, automata theory, formal verification, synthesis, all of that. So, Akshay, floor is yours.
Thanks, Supratik. Thanks for that very kind introduction. Let me quickly share my screen. Are you able to see my screen?
Yeah.
Okay. All right. So thanks, Supratik. Thanks, everyone, for this nice chance to talk to people in the SAT+SMT workshop. Today's talk I'll be giving is on synthesizing Pareto optimal interpretation for black box models. So it's really in the intersection of formal methods and machine learning. And this is joint work with Hazem Torfa from Berkeley, Shetal, Supratik and me from IIT Bombay, and Sanjit and Hazem are from Berkeley. So it's really a collaboration between Berkeley and IIT Bombay. And this was presented at FMCAD 2021. So this is a paper which is accepted in FMCAD 2021. Also, these slides have been made by Hazem, and I have just kind of borrowed them like verbatim. So if there are any problems in the slides, please write to Hazem. If he was there, he would have given this talk, but he's not around, so I'm giving this talk, right? All right, so let me go on with the talk. So let's start with a kind of a problem of like, kind of a hot problem in today's world, which is on about the pervasive use of machine learning, right? And we know that there are several machine learning components which are getting more and more applied in many different areas, right? Increasingly on different domains, especially even in domains where one historically thought that trustworthiness or accountability was a major issue. Like it could be a safety critical domain, it could be transport, it could be healthcare, or it could be like security critical applications. It could be e-commerce, it could be like say social media, or it could be some finance things, like maybe you're making some decision on bank loans or mortgages. So these are clearly domains where you need a certain level of trustworthiness and accountability, and nevertheless they have been what shall I say, flooded by machine learning components because of their usability and for various reasons, right? So the point is that the components which are used, like deep neural networks, are very complex models, and as a result, they are hard to comprehend. And because of their pervasive use in such kind of critical applications, it has become very important to explain this unexplainable model or this hard to comprehend model. And it is not only a question of ethics or morality, it is also becoming more and more a legal issue, right? So there are these emerging laws in various parts of the world. I don't know about our country, but other places in the world where it is important to be able to guarantee or to be able to at least explain why a certain machine learning component behaved in a certain way. So that's really the question where we are starting on. And this is basically asking for tools which can not only synthesize an arbitrary interpretation of the ML component, but actually give an interpretation or an explanation of the ML component which has a formal guarantee on its correctness. Okay, so and then we will formalize what this notion of formal guarantee we want it to be, right? And that's kind of the goal of this talk. Okay, and when we are looking at such synthesizability of explainable models, actually there is a very rich history of work. Okay, and I mean very recent work, but a very rich history nevertheless. And there are this whole series of works which talk about synthesis of optimal models, and these could be graphical explanations or graphical interpretations like decision trees or linear models, or it could be more textual interpretations like decision rules, right? And I mean, we've cited one or two of these, but indeed there are a huge number of such works. And in fact, I would point any interested reader to these two surveys which have come out recently, which talk about explainable artificial intelligence and various types of interpretability or explainability. One thing which is common to all of these approaches are usually based on a single objective formulation of the problem, right? So they say, okay, make this as accurate as possible, or they say, okay, fix that there are 5 nodes in your tree, but then make it as accurate as possible. So there is one, what shall I say, one objective which we are a single correctness measure which you are trying to optimize, right? Maybe it may be a misclassification rate or whatever it is. And even a more richer notion of what is called the structural risk minimization looks at 2 orthogonal measures, one depending on the structure and one depending on how well it explains the sample set, but then it finally combines them into a single metric and then tries to optimize that. Okay, but the point is, or kind of our view or our thesis is that interpretation synthesis is actually not necessarily and not always a single objective optimization, because you do have a kind of a trade-off which is inherent between correctness and explainability, when importantly, we are looking at black box ML components, right? Where we don't know the hidden structure of this ML components, then maybe we want, maybe we have a very nice explanation possible for the black box model, but maybe it's not always correct. Or maybe it could be that the black box model is explained by a very correct explanation, which matches on all the sample points, but then it is not very explainable. That is, it is not very human readable or human comprehensible. And this leads to, in some sense, the idea of multi-objective optimization. So essentially and when we are talking about multi-objective optimization, where we have these two objectives of correctness and explainability, we naturally land upon the idea of what is known as Pareto optimal interpretation. An optimal interpretation, which we are not saying that it is with respect to one objective, but with respect to this Pareto optimality between these two objectives. So, so this is kind of the main, what shall I say, difference that we are looking at with respect to the existing work. And that kind of brings me to the outline of the talk. Okay, so what we will do is first we will give a concrete example of what I mean by this Pareto optimal interpretation synthesis, and maybe I'll spend almost like 3-4 minutes on explaining this problem as well as giving the formal definition. Then we will go into the three technical contributions. I mean, I would say the first contribution is even the problem definition in this way. And then we go into the three algorithmic solutions. First is to come up an algorithm that we have developed to come up with one interpretation, which is Pareto optimal. Then how do we go from there to exploring the entire space of Pareto optimality? And finally, all this initially will be with respect to the set of samples. What can we, how do we generalize that from set of samples to the entire black box model itself? And for this, we will use classical ideas from statistical methods. And finally, if I have time, I'll look at a couple of experimental results and I will stop. Okay, so the motivating example. Are there any questions here? If not, shall I go ahead? All right, no questions, so I'm going ahead. All right, so let's consider this example of a auto taxi. So what we mean is a flight controller, which has an ML-based perception controller, which works in the flight. And as you can see, actually there's a nice video which I'm not able to show it here. But essentially, there is a controller which is sitting here and which takes decision on taxiing of the plane, right? Where it taxis and whatever. And there is a decision module which says, when can I give the control to this perception-based, ML-based perception controller, or when should I take over with manual control? Okay. And actually, when you run this on this taxi, so what are the components for which the ML component will work on? Well, they could be weather conditions. So for instance, it could be whether it's cloudy or it is clear. It could be the time of day. Is it morning, afternoon, or evening? And where is the initial position? Are you near the, I don't know, near the, whatever, at the edge of the line, or are you in the center of the track, right? So these are the three decision modules, or the various predicates on which the ML component makes its decision, right? And the decision module trusts the ML component based on these predicates. These are the factors under using which it's going to make this decision. So when we run this, what we find is that the first in the first run here, actually this can't be seen very clearly, but there is a point at where the decision module concludes that this particular set of predicates or the values for the predicates will result in the flight controller not making the right call, and therefore it's not a valid one. That's this red mark. And vice versa, in running it again in another module, it says that, okay, no, this is fine. With green, you can go ahead. I think this might be switched. But yeah, these are the kind of results. This is a little bit more impressive with the video, but trust me that this is what we are trying to talk about. We are talking about two different situations where a decision module, which is a black box module, behaves differently based on some bunch of predicates. And now the question is, why did it do this? what was the reason why the decision module predicted this way in one case and predicted the other way in the other case, and can we somehow give an interpretation for this. And the class of interpretations that we look at would be decision diagrams, and which is a slight generalization of decision trees. And the predicates for this particular example will be clouds, rain, initial position, and the time of the day. Time of the day could be morning, afternoon, evening, dusk, or whatever, midnight. And explainability will be a score which is based on not only the number of nodes which are there in the in our decision diagram, but also in weights somehow associated to the used predicates. I won't go into the details of this. You can look at the paper, but it's basically a combination of which predicate is more important and a favorability measure on the predicate and the number of predicates which are used to explain this, right? And finally, the correctness is a prediction accuracy with respect to a given sample set. So you have a bunch of samples of these runs of this module, and with respect to that, we should be able to predict accurately. So when we run this, here is one example of a decision diagram. So in this decision diagram, for instance, I have that the correctness measure is something like 0.94. What this means is with respect to my set of samples, whatever this guy predicted matches very closely. 94% of the time, it matches with the samples, what the sample said. But unfortunately, the explainability predicate is 0.71, which is less than. So what this means, I mean, for all that you care about right now, could be that this is, from this, we can't really figure out what was the main reason for this decision module taking these decisions. Because let's say this graph is too complicated, and maybe you want a simpler explanation for it. So you can go ahead and ask our tool that, okay, give me another interpretation of what happened inside the decision module, but this time make sure that the explainability score is high. So you run it, and it throws out another one. And this one is just saying that it only depends on time. In this time between 8 and 12, there is no alert, whereas if the time is at night, there is an alert. Great, time makes a difference. But unfortunately, though the explainability is high, because you look at this picture and you know exactly what's happening, the correctness or the matching with respect to the sample set is not very high. It's only 0.6. 61% of the time only it matches with the what the sample set said. So in this case, we can go back and ask, saying that, okay, no, but we don't want it to be so bad. We want something better than this, but at the same time to have a high correction, high correctness value as well. And then our tool would return an interpretation, something like this, which is somewhere in between, where the explainability score is also high and the correctness score is high, and at the same time both of this happens. And indeed, looking at the picture, maybe you can intuitively see that what it says is that either the position and so there is a time and there is a position, both of which together make some impact on this. So these are the kind of sensitive parameters. So if you are at night and if your position is far away, then maybe you should be alertful and you should not allow the so this is what the decision module has predicted. Okay, so this is kind of the idea that we have. The important point I want you to take away from this slide is that there could be multiple interpretations for the same phenomenon, and they could differ in terms of the explainability and correctness metrics. And this brings us to the problem that we have to formally kind of formalize here. And this is the Pareto optimal synthesis problem. So Pratik, how many minutes do I have?
Maybe 3 minutes.
3 minutes. Okay. So let me quickly at least define the problem formally. So we have a set of a syntactic class of interpretations, which is decision trees, decision rules. So this is nothing but a function from input to outputs. We have a set of samples, which is again a subset from the same set of input outputs. And we have an explainability measure, which, as I said, is from the set of interpretations. It assigns a measure to each one of them. And we have a correctness measure, which looks at each interpretation. It looks at a set of samples, and then it gives you a value saying, how close is this to being correct with respect to this set of samples. And what we want as output is one Pareto optimal interpretation, which maximizes, which gives the argmax or the Pareto optimal between these two measures. Okay. And the way we solve this, so to get one solution to the Pareto optimal synthesis, as I said, what we use is weighted max set. In this community, I guess we don't need to introduce weighted max set. It is the problem of taking a formula and trying to find an assignment which maximizes this quantity, which is the weighted sum of the clauses, right? And the way we encode this, I'll let you go into the details in the paper. But essentially, the idea is we have a couple of predicates, a couple of formulae which will encode the syntactic class and the samples, and there will be a set of unit clauses which will encode the correctness and explainability measure. And that will be the quantitative part, and this is the qualitative part. And in some sense, we build the final formula by taking the conjunction of all of them. So indeed, by assigning some appropriate weights to the clauses, right? And the Pareto optimal interpretation is really looking at the sum of the correctness, maximum sum of the correctness and explainability score over this. So that is the weighted max stat problem which we define. So for the details of this, I refer you to the paper. And once we have this, then we look at the problem. This is how we synthesize one Pareto optimal interpretation. And from there, we go to, I mean, again, I don't want to go into the details. The basic idea is that every Pareto optimal interpretation can be thought of as a point in this space. And what is the guarantee of being Pareto optimal? It is that there is no Pareto optimal point in this part, in the red part, right? And for every point here, there is this guy dominates that. So this is better than all of them. So in other words, once I get a Pareto optimal point here, what we do is we recurse and then we go into the other to R3 and R4 and ask if there are further Pareto optimal points there. And we do this recursively until we get all the Pareto optimal points. Now, one caveat is that we don't want to actually do this for, we don't want to recurse by changing the correctness measures, because the correctness actually depends on the set of samples. We want to do this by only kind of modifying the parameters of the explainability measure, because that depends only on the problem input, not on the set of samples. And how we do that is kind of the technical part of how we synthesize the set of all Pareto optimal interpretations. So I'll skip that. And finally, just to kind of give a heads up to those who know, there is this very nice theory of how to obtain statistical guarantees from a set of samples, where the problem is basically that from an exhaustive set of samples, I mean, it's often not practical to have an complete or exhaustive set of samples. So as a result, we need to have some statistical guarantee saying that, okay, if your sample set is at least this high, then actually you can make some statement with respect to the entire black box model. And for this, we go into the idea of probably approximately correct or packed learnability. I won't go into this at all right now, so I'll skip this slide. But that gives us basically, brings me to the experimental slide. So Pratik, I'll take one more minute and I will stop. Is that fine?
Sure. Yeah.
Okay. So let me just flash some slides. So on the experimental results for this nice auto taxi model, for instance, this point is exactly this Pareto optimal point with 0.71 on the explainability score and 0.94 on the correctness score. This point was the one that we had, which was intermediate, right, between 0.89 and 0.9. And this one was the very good explainable, but not very correct model. So as you can see, there were many points, and this gives the user the ability to pick whichever point suits that person for their application, right? And you can really, I think this is kind of the USP of this work, that it allows us to, the user to tune the interpretation with respect to what they are looking for. And within that, it gives Pareto optimal points. So you cannot improve that if you want to improve both of them at the same time. At least one, it must be optimal. Right? We did this on a couple of more benchmarks also, one with respect to bank loan and another one on theorem provers. I won't go into the detail of all of this, but they are all there in the paper. Please take a look at it. And we also ran, so we kind of have some experimental results to say, it's how the time varies with respect to how many Pareto optimal points are there and how do we kind of, on an average, how do we perform for each point, right? So that brings me to the summary, which is basically that when we are looking at black box models, we probably should be looking at Pareto optimal interpretations rather than just interpretations, because Pareto optimality is pretty much the best you can hope for in black box ML models. And we kind of give a max SAT solution for, one important restriction is with respect to a finite domain for computing one PO interpretation. And then we kind of generalize this to kind of say, to have an algorithm to explore the entire Pareto optimal space. And then we used existing statistical guarantees used on based on pack learnability to generalize to the entire black box space. And I leave you with the reference to the paper. This is the archive version of the paper. Thanks. Yeah.
Thank you, Akshay. There are any questions? We can quickly take one or two of them. Unmute yourself and ask.
So I can't see anybody. So if somebody is asking, please unmute and ask. I won't know if you're lifting your hand.
Yeah.
Hello.
Yeah.
Go ahead.
Yes, sir. What I wanted to ask, this is more the duality or this conflict is more between accuracy and explainability, right? Rather than correctness and explainability, because somehow I can't think of any explanation that is not correct and still like it explains something nicely.
Correct. Accuracy is
accuracy over the samples here.
Correct. So you're saying that the word should rather be accuracy, not really correctness.
Yeah, it is just accuracy over the sample that we are.
Yeah, but with the statistical guarantee saying that it can be used to infer accuracy or correctness over the black box model itself.
Okay.
Right. Essentially, the idea is that basically, if you have a big enough sample set and you have sampled it correctly, then you can actually generalize to the entire space itself. That's what we are saying, right? With some epsilon delta guarantees. That's the pack learnability.
Yes.
Yeah, but I think it's a valid point whether it should be called accuracy or correctness, and I'm not sure which is the better term. That's a separate point to discuss.
So Akshay, So Akshay Madhukar here. I had a question. Yeah. So this notion of explainability that you spoke about, it looked like a syntactic notion of explainability. Do things change when you have a more semantic notion of explainability?
So what?
As in, as in you said that something is more explainable if you have a shorter, as in a smaller tree or something.
So that's basically what we are saying is that we need to define some metric for explainability, right?
True.
And that metric is over the given set of predicates.
True. So that's what I was wondering. So if you define a different metric for explainability, will this framework still work? As in
I mean, well, as long as you can encode it into SAT or into max SAT, yes, it will work.
Correct. So in fact, that's the question that I was coming to. So if you have more semantic notions, do you think you can still encode it as a max SAT problem?
I guess that depends. I don't have a very concrete answer to your question. I guess it will depend on what kind of semantic constraints we are talking about.
Okay.
But maybe there are applications for which you will need a more semantic notion which cannot be captured using our framework. Yeah, that should be possible.
Sure.
I don't know whether there's a more comprehensive answer to that. So Pratik, do you have anything else to weigh in on that?
No, I think the explainability will change.
Depends.
We have more semantic features. And I think encoding will be very different. And we don't know how it will look like.
Well, it's a nice question. Thanks, Madhukar.
Thanks.
Okay. Any other questions?
Okay. So thanks, Akshay. And then we come to the end of this part of the session, and slight overshoot. So we'll reconvene back at 5:30. That's the time for Marayan Hule's invited tutorial. So he's of course one of the topmost experts in the area of SAT solving. Lots of foundational work he has done. So I encourage all of you to be back in about 5 minutes.
6 minutes.
6 minutes, okay.
Yeah.
Okay, so we'll see you at 5:30 Indian time. Hi, Marayan. Great to see you.
Hi, Supratik. Good morning or good afternoon, good evening for you.
Yes, good morning for you. Let me make you co-host so that you can share your screen. Okay, great. So do you want to share your screen just so that we make sure that there are no technical glitches?
Yeah.
Yep, it's fine. Perfect, perfect.
Yeah, this looks good.
Yeah, perfect. Okay, so it's fairly early for you, but we're really thankful that.
Yeah, no, yeah, it's difficult to have a common time, right? It's the time zones are not really well aligned.
I know. Thank you for agreeing to give the talk at this hour.
Yeah, no, I'm looking forward. Hi, Kuldeep.
Hi, Mara. I think this is the only thing for which you wish Earth was flat and there would be only one time zone.
Yeah. Because it's 5:30, right? Or
yeah.
It's 5:30 p.m. here.
Yeah.
We also have participants from Singapore and China. So
yeah.
It's later in the evening for them.
Yeah. No, it's yeah. So it reduces travel, but it's also in other ways less convenient. Yeah. So how many people have been participating on average?
It has been fluctuating. People have been joining, leaving. There are also people watching on the YouTube channel where it is being live streamed. So yeah, it keeps increasing, decreasing, and then.
I think for the tutorial yesterday, we had 30 people, if I.
Well, at the peak, we had close to 50, I think.
Yeah, at the peak we had. But I thought 30 were kind of consistently.
Yeah, 30 was, yeah.
So, and if I do this, you see my screen? My
Yes.
Yeah.
Okay. Very good. So, how many times have you now organized this Indian SAT+SMT school?
This is the 6th edition.
Oh wow!
This is the 6th year. So
cool.
Yeah, I think we've been fortunate to have great speakers in all the editions. So we have a website for the winter school.
Yeah.
And that lists all the, it basically archives all the websites, all the web pages for the previous editions. So.
Yeah, no, I've been looking at it. I was not aware that there were actually already 6.
Yeah.
Yeah, very good.
Yeah, I mean, it's of course much more fun if we have it in person, face to face. But hopefully next year will be face to face.
Yeah, it's hard to tell, right? How things will evolve. It seems that this pandemic goes on forever, right?
Yeah.
Yeah. No, far from ideal, but yeah, let's see. I hope to see both of you at Flock.
Yeah.
That's the hope for Flock.
Yeah.
Sorry, what did you say, Kuldeep?
That's what we hope, that Flock
Yeah.
would be in person.
Yeah, but I think Israel is now, fully closed, right? You cannot. I think as foreigners cannot enter the country at this time.
Oh.
Yeah. keeps changing, right? I mean, almost every month there is a new situation.
No. Yeah, no, this is far from over. But yeah, let's hope things will improve. Typically, I think with the warmer weather, it's better. So let's see. Because are the classes there all in person?
No. I mean, this semester, until the last semester, the semester which just ended, everything was online. We were hoping that this semester we would be back face to face, because more than 50% of our students have been able to come back.
Yeah.
But it's still, around 40% are still not here. So we can't have face-to-face classes. So some courses will be face-to-face if all the students enrolling in that course are already here. But other courses will be online. I mean, there was a proposal for having it in a hybrid mode, but I don't think anyone is venturing for that, because the logistics for that is just, horribly complex. You have to have.
Yeah, I have been teaching, so both my graduate and undergraduate course have been in person this semester.
Great. Okay.
Yeah.
So all the students are already coming.
Yeah, so all the students are there. Yeah. So I think only for some really big courses where they cannot fit people in the room, that's hybrid. But I think all the smaller courses are in person.
Yeah, in Singapore, I taught the spring semester in person and fall was remote online. So, during spring, it looked like fall would be in person, and then the number of cases increased and we had to go back to be online.
How is the situation in Singapore now?
Now we had the worst wave in last 3 months or so. So the number of cases due to Delta went up very high, but now it seems to be coming down, and hopefully Omicron would not cause havoc.
Yeah.
So.
Yeah, here in Pittsburgh, I also have seen the cases are going up again. So let's wait and see.
Yeah, and there are lots of Greek letters left. I hope they're not used.
Yeah, we're now halfway the alphabet.
Yeah.
At least I learned Omicron. I did not know the word Omicron until now.
Yeah, it's typically a letter you don't use in the scientific publications, right? Since it's just the O.
Yeah. So, Kuldeep, maybe we can gently get started.
Yeah, I guess. Hey, good evening, everyone. So welcome to Day 2's tutorial. It is our great pleasure to have Professor Marayan Hule as the invited speaker at SAT+SMT Winter School finally. We have been wanting to have him as speaker for a while. And pandemic made things work out. So Professor Marayan Hule is an associate professor at Carnegie Mellon University. He received his PhD at Delft University of Technology in Netherlands. His contributions to automated reasoning has enabled him and others to solve very hard problems in formal verification and mathematics. His recent contributions to computer-aided mathematics involve solving the Pythagorean triple problem, the fifth Schur number, and Keller's conjecture. He has co-authored 8 award-winning papers and has developed award-winning set solvers. His pre-processing and proof-producing techniques are used in perhaps almost all the state-of-the-art set solvers. And we are going to learn much more about the proofs of unsatisfiability that he's going to talk about today. He is also an editor of Handbook of the Satisfiability, which is the standard in the SAT community, and is a tremendous resource to almost all of us, whether we are starting our career or in midway. So with that, we are very happy to have Maran you over here, and I'll turn over to you. Thanks for giving this tutorial.
Kuldeep, many thanks for the introduction, and also Kuldeep and Supratik, thanks for the invitation. I'm glad to be able to finally speak at the winter school. So for anyone who is comfortable with it, please just turn on your camera. Also, that makes it a bit more interactive. So the tutorial consists of 2 parts. The first, both are about proofs of unsatisfiability. The first focuses on applications and theory, and the second part about verification and beyond. The first part, I will only use some slides, but I will give all kind of examples of how to use proofs in the second part. If you want to kind of work with me, you don't need to, but if you want to kind of see, use everything, then go to the repository shown on the slide. And if you clone that one, you should be able to follow everything that I'm doing. Oh, that was not the intention. Why is it not advancing? Okay, space. So the first part will consist of these 5 parts. So first I will have an introduction, then I give some examples of proofs, and then I will go more into details. What is actually a proof of unsatisfiability? There's various systems in which you can express them. I will especially talk about the more expressive systems. And the last part of the first half, I will talk about proof production, and not only of sequential solvers, but also from parallel SAT solvers. Okay. So this slide is probably, doesn't need too much explanation. Since you're here at the summer school or the winter school, you already heard a lot about positives about SAT and where it's used. So there are many applications ranging from formal methods. It's used in industry a lot, to security. For example, SAT solvers have been used to compute the first SHA-hash collision. It's used in bioinformatics, lots of planning and scheduling. So these were kind of the early applications of SAT. Also, one of the very early ones was for train safety. So I think in 1980, one of the first SAT solvers was actually used to improve the safety of the Dutch railways. It's used in all kinds of other tools, like, for example, in first order fear improvers. So in all kinds of automated fear improving. There was also a couple of years ago, there was a DARPA challenge to generate exploits. The winning team used a lot of SMT solving, and there has also been areas where it seems to kind of unlikely that SAT would be useful, such as term rewriting termination. These are problems that are potentially undecidable, but SAT solving really was a kind of a key technology of improving that results in that field. So how does it work? We have these problems in all kind of these areas, and then we encode them into propositional logic, run the SAT solver, and then decode the solution. And I already kind of mentioned it when talking about formal verification. This technology is used heavily in industry, for example, at the companies shown on the slide. let me kind of highlight one of these applications in particular. So equivalence checking. What you have is that, for example, a company like Intel, they have a circuit at the beginning of the day, and then lots of engineers improve it, and at the end of the day, they have an improved circuit. And then the question is, okay, are these two equivalent? Did nobody make a mistake, right? And how are you going to test this? We're going to test whether for all possible inputs for both circuits, there exist an outputs in which they differ. And in order to make sure that that both circuits are equivalent, the answer should be no. There should not be an input such that the output is different. And so if we want to, the expected answer or the desired answer will be unsatisfiable. And because unsatisfiable means equivalence. And what we don't want is that such a claim of correctness, which is from the SAT solver, is based on a bug in the SAT solver. So it's very important that SAT solvers are used to show that things are correct. It's very important that to know that actually that the claims that the SAT solver gives are that we can really trust them. However, SAT solvers are complicated tools, and probably anyone who wrote code knows that as soon as you write more than say 40 lines, there's probably a bug somewhere. And it's also well documented that that automated reasoning tools give incorrect answers. So there have been, for example, papers a decade ago that there are bugs in SAT solvers. There are actually many more bugs in SMT solvers. QBF solvers or QSAT solvers have really made big steps towards correctness, but especially in a couple of years ago, it was more like an educated guess than that it was that you could really trust them. So that the community actually doesn't even use the term bug, they use discrepancy, which means that you are disagreeing with the majority of the solvers. And so what I also mentioned earlier, right, is that SAT solvers are used in industry for all kind of correctness checks. And we really want to make sure that none of these claims are due to bugs. What I frequently have been hearing is that, okay, tools might be buggy, but this is typically the weak tools that are buggy. The top tier solvers, the ones that are winning competitions, they are not buggy. This is really not the case. From all the competitions that are related, it is known that winners have been buggy. For example, there was the hardware model checking competition. There was a benchmarks with which you ask, okay, is there an input for the circuit such that you can trigger the wrong output? And the top tier solver says, okay, yes, for this circuit, this is possible. Only it couldn't provide the input that actually would result in the wrong output. And the solver was that the result was considered correct. The next year, the same tool was also the only one able to solve it, but now it said that the circuit was correct. And again, it was considered the right answer. And so, and I've seen it now in various other ways that tools have been buggy. And one of the reasons is not only implementation bugs, but because the tools have been coming faster and faster, and all kind of new techniques are introduced. Many of the bugs are actually conceptual errors, techniques that are not sound. They seem to work, and they apparently work in many cases, but not always. And one of the things what we did to counter or to improve the correctness is to make proofs of unsatisfiability mandatory in some competitive events. And not only does industry really want to have a stronger justification, but also various other communities, like, for example, the math community. I will also talk about various math results that have been obtained using SAT solvers. And the math community does not only want to say, okay, oh, a tool said either yes or no. They want to have an answer that is verifiable. So you can also ask the question, okay, so since verification is that important, why actually are you using proofs? Why are you not just simply verifying the tools? So this might sound like a promising idea. However, verifying a tool is a daunting task. So the tools are optimized and modified constantly, and if you would prove things to be correct, you constantly need to modify the proofs to kind of have the proof of the latest version. And frequently, it is not really known why the tools are correct. So one of that is Lingeling, a solver by Armin Bieren. He called it experimentally correct, which means that he ran it on 1 million small instances with another solver that he trusted, and on all 1 million instances, there was the same result. However, after looking carefully at the code when I was doing a postdoc with him, I noticed that there was actually a 7-clause formula on which it would give the wrong answer. So even if you know that it works correctly for 1 million cases, you're still not sure whether it's correct all the time. But that doesn't mean that people haven't tried, right? There actually have been various attempts.
Marijn,
yeah,
unfortunately my camera seems not to be working, but I just wanted to check, I just wanted to ask that how did you go about finding that 7-clause formula? I mean, was it like delving into the debug traces or something? Or?
No, I was suspecting this. So this was I was suspecting something was wrong, but I couldn't really figure it out. And then I really looked at the code, what it was actually doing. And so I don't know if any of you have looked at SAT solving code. Catecol is highly suggested to look because it's well written. Lingeling is way harder to read. But so by understanding why it was probably wrong and looking at the code, was able to kind of figure this out. But there was already a strong suspicion that there might be something wrong. Potentially, yeah.
Okay, yeah, amazing stuff.
Thank you. And so people have been trying to verify solvers, and there have, for example, the two kind of famous algorithms, DPLL and CDCL. I will talk about more about CDCL later. Both of them have been verified. They're verified implementations. However, they are not really efficient. And so if you look at kind of what we have today, is that if you have you solve using state-of-the-art tool, you use proof logging, and you do proof verification, possibly even with a formally verified verification tool, this is much faster compared to running any of the verified solvers. So this is kind of, so although proof logging and proof verification add some overhead, but this overhead is much smaller than any of the cost of actually implementing it efficiently in a fair and proving system. And the nice thing about the proof logging approach is that you can only need a single verifier that can validate the results of many of the solvers. By the way, if anybody else has questions, feel free to ask or interrupt at any point. I will be happy to have some interaction. So that was kind of the initial plan that we had, is to, okay, let's have proofs. But there were various challenges, and so I will also talk about them more during this tutorial. First, there were theoretical challenges. So some various kind of problems that appear simple. It's known that they have exponentially large resolution proofs, and solvers have been integrating dedicated techniques to quickly solve these problem classes. And if we would express everything in the resolution proof system, I will talk about resolution in a moment, that would mean that the proof could be exponentially larger than the runtime of the solver. And this is something you really don't want. So what we wanted is that if you have proofs, then the proofs should be kind of linear in size of the runtime. And so what was needed was a proof system to compactly express all the things that are going on in state-of-the-art SAT solvers. And I will talk about this proof system later on. Another challenge was of practical nature. So there have been proposals, I think, since the early 2000s to have proofs for SAT solvers, but they all kind of failed to kind of really be adapted by the tools because of the complexity to integrate all the proof logging and the overhead if you want to, say, express everything using resolution steps. And it was very difficult to convince all the developers to kind of support a single proof system and logging. And so one of the things that we changed is that instead of having very detailed proofs, we actually have proofs, and this will become more clear later, is we have proofs that are relatively compact. So as soon as a solver learns a clause, it just tells the checker, okay, I was able to learn this clause and you figure out how I did it. And so the computational burden is no longer on the solver to really express to the checker, okay, has been things, why can this clause be learned? No, it's just, okay, the solver learns it and the checker needs to figure out how to do this. And so we have efficiently checkable redundancy property, which the checker can do efficiently. And I also wrote a reference implementation for the mini-SAT based solvers, and most of the SAT solvers that are used are based on the mini-SAT code base. And by making a reference implementation, it was very easy for tool developers to use it, because they could just run my patch on their code, and then there was proof logging was enabled. So I don't know whether you have seen already such a plot. This is cumulative solving distribution plot, and this shows all the winners of the SAT competitions starting from 2002 to 2020, and all of them running on the SAT competition 2020 benchmarks. And what you see here is, this is the CPU time, this is now the number of instances solved. And for example, in 1,000 seconds, Limmat is able to solve about, 15 instances, while the last year's winner KISSET was able to solve about 175. And so what we've seen in the community is that solvers became stronger and stronger, but also when we did this experiment, so I did this together with Armin to kind of look at the winners and how they behave, but also when you do this, you see that the earlier solvers, they have been quite buggy, and we detected lots of bugs in earlier solvers. And so not only is there clear progress in performance, but there also has been clear improvements in the correctness. And this is mostly thanks due to proofs. And in the second part of the tutorial, I will also go talk about beyond proof checking. So proofs are very useful to say, okay, is the result of the SAT solver correct? But there's many things more that we can extract out of the proofs. And so one of them is, for example, unsatisfiable cores. So unsatisfiable core tells you, okay, so the formula is unsatisfiable, but actually there is a small core which is also unsatisfiable. This can be very helpful to know, okay, what is the cause of unsatisfiability? And there are various other solving techniques, in most particular MAXSAT, which crucially kind of depend on cores, and they can use these proofs to extract cores for the solving part. Another thing what it's useful is for crack interpolance. This is an important model checking technique. However, it requires resolution proofs. So I will talk about more general proofs in a moment, but it's not fully clear yet how to kind of use these proofs when you want to compute crack interpolance. And another thing what I also will talk about is the proof checker cannot only check the proofs, but it can also optimize it. And what we have seen is that in many cases, the proofs, there is a lot of redundancy in it. And so only a small part of the proof is actually required to show the unsatisfiability of the formula. And there, so for it also for me, and I will also talk about it at the end of the second part, is that optimized proofs can be really help you to kind of understand why a problem is unsatisfied. Okay, that concludes the introduction section. Are there any questions?
Mary, you mentioned that even though we can verify the result of CDCL or TPLL, but CDCL is not efficient. What do you mean by not efficient here? Because we know that current CDCL solvers are all based on this framework.
So what I was mentioning here is, so the versions of, so the solver, there is a solver in TPLL that has been verified, and also a CDCL solver that has been verified. But in order to verify it, you have to write code that cannot go really too much low level to have the real performance that you want. So so in order to reason about why a solver is correct, you have to kind of turn off features to make, or low level implementation techniques to kind of show that it's correct. And this really slows down the solver. While if you have proof logging, you don't need to turn off anything of the solver. You can just simply use the solver and all the low-level techniques. And because you only care about, you only check whether that given result on a single instance is correct. Is that clear now?
I don't understand the first statement that I know we can use the proof logging and proof verification, and it's much faster.
Yeah, but do you also understand why it's why it's difficult, why verified softwares are less efficient?
In further, you say that you decided we cannot dive into the low level part. What's the low level here?
Yeah, so of course it might be possible to validate everything, but it is so as soon as you start verifying low-level implementations, it requires a lot of effort. And especially since the solvers are changing all the time, it is really not something that you want to invest in.
Oh, you mean the low level, the practical implementation of the SAT solver?
Yeah, so there are all kind of so if you look at the source code of the solvers, there's quite some tricks down there to kind of make it efficient. Yes. And these tricks are, it's difficult to reason why these tricks are correct in a fair proving system.
But the proof for the CDCL is based on the resolution. We only have to check the resolution. We don't have to check the heuristic is correct.
No, so heuristic. So if you don't have to. So of course it all depends how you do the verification. But typically the heuristics you don't need to kind of show correctness, because you kind of show that for any heuristic it kind of works. Yeah.
Okay. Thank you.
Okay.
So, Marian, there's a related question on the chat.
Yeah.
So Dennis Yurichev is, I guess, asking a similar question: that are you testing the SAT solvers, or are you doing something different? So I guess we're not testing SAT solvers, right? We are testing the.
So no, what we're not testing. So with the proofs, we're not testing the solver. So the solver is going to produce a proof. So you give the solver a formula, and the solver returns a proof, and then there is a separate program that takes as input the formula and the proof, and it says it checks whether this is indeed a correct proof to show unsatisfiability of the formula. And so for each result of the SAT solver, you have to do this again. So in the kind of the follow-up question there, in an ideal world with a bug-free SAT solvers, would you need this? No. In case you would have a bug-free SAT solver, you wouldn't need this. Although it's very difficult to kind of make sure that the SAT solver is bug-free, and so in practice it's much more effective to okay. So we don't care whether the solver is bug-free, or it can use all kind of techniques that might be even unsound, as long as it's able to produce a proof which we can independently check with a checker that we do trust. We don't care what goes on in the solver. The solver was able to produce something which we can use to check, and that's all we need.
Yeah, I think, yeah.
So I see a raised hand.
Yeah, that's me. Am I audible?
Yeah.
So I just wanted to check if I understood this correctly. And like looking at it from the perspective of the SAT solver developer, there's no extra effort or no extra logging effort that needs to go into sort of these satisfiable instances, right? So for example, if there's like some arbitrary decisions, like, I don't know, for instance, face saving and stuff like that, and these only are relevant for the satisfiable instances. And so there's no additional effort that needs to go into logging these tricks or these steps. Is that right?
So
or
yeah,
is the question clear? Sorry.
Yeah, no, so for the set assault, we have the reason why we need proofs of unsatisfiability is because checking unsatisfiability is difficult. For the satisfiable case, it's easy, right? And so for satisfiability, if you have a satisfying assignment, right, it's also kind of a certificate or a proof that the formula is satisfiable. And this can be easily checked, right? You just give all the variables their assignment, and then you check whether in each clause there exists at least one satisfied literal. And so for the satisfiable case, you need to produce a satisfying assignment. And as long as you're able to produce a satisfying assignment, then you're fine.
So I think maybe I can make this a bit more clearer. So like during the run of like one SAT solver on one particular instance, it's not known beforehand whether it's a satisfiable or an unsatisfiable instance. And so the SAT solver takes certain steps. Like I think the best example I can think of is like phase saving, for instance, which is geared specifically towards the satisfiable instances, right? It has no impact if the final solution is that the instance was unsatisfiable. So what I'm trying to understand is there any extra effort that needs to go into even logging these steps, this phase saving steps, because we don't know at this moment if the instance will turn out to be unsatisfiable.
So one thing that needs to be done in the satisfiable case is, so when you so the solver does not only search for a solution by just trying assignments, it also heavily modifies the formula during the solving. So variables get eliminated and all kind of other things are happening. I will also talk about it more later. If you eliminate a variable, right, or do something else that changes the solution space, then you do need to record it in order to kind of, once you have a solution for the formula that you in the end say, okay, this formula is satisfiable. That is a different formula from the formula that you started with. And the solution that you have for this formula over here might not be a solution for the formula over there. And so you do need also for the satisfiable case, record the transformations such that you can do the transformations back to get a solution for your original formula.
All right, okay.
Yeah?
Yeah, that answers it. Thank you.
Okay, thanks. So there is another question in the chat. Are verified tools guaranteed to be error-free because their verification process may have been buggy? So how much extra confidence does having a proof and it being verified gives? Is there some metric? So I don't know whether how many students actually have been working with fear improving systems, but it's very difficult in a fear improving system to prove something which is wrong. And so once you kind of work with these tools, then you kind of need to explain to the computer why it is correct, and then you constantly encounter things like, oh, I didn't think about this or aspect or this aspect. And so although there might be, so the verified tools, so it depends on the system which you use to verify it, they have a trusted core, which is kind of everything that the small part of the tool for which there might still be errors. But it's extremely unlikely. And so as soon as you have a verified tool, you only need to trust that the trusted core is correct of the tool in which you developed it. And once you, for anybody who kind of has experience with this, it's very difficult to kind of and almost practically impossible to prove something that it is incorrect. So you have very high confidence. Okay, now to the second section, which is some proof examples. So here I will talk about some mathematical problems that have been solved using SAT solvers. Oh, you have another question? Is he here? Okay. No, there was in my screen. There was again the raised hand notification. So let's look at first one problem. So this is a problem. Oh, sorry. This is where structure you should read red. So we have all the integers, and we are going to color them with two colors, red and blue. And we wonder whether it's possible to do this in such a way that there is no monochromatic solution of the equation of the equation A plus B is C. And so let's look at A plus B equals C for the integers 1 to 5. And there are 6 such solutions. 1 plus 1 is 2, up till 2 plus 3 is 5. And now let's try to color them with two colors, red and blue, such that there is no monochromatic solution. So all the 3 numbers have the same color. So without loss of generality, we can assume that one is color blue, because so at this point we didn't use red or blue, so we can now say, okay, the first number is blue. That means that 2 must be red, otherwise 1 plus 1 is monochromatic. Now 2 plus 2 is 4, and so in order to avoid a monochromatic solution, 4 has to be blue. Now what we see here is 1 plus 3 is 4, so 3 has to be red. 1 plus 4 is 5, so 5 also has to be red. But if both of them are red, then 2 plus 3 is 5 are all red. So if we color the integers with two colors, red and blue, then we will end up with a monochromatic solution of A plus B is C. Sure.
Maran, for the 1 plus 2 equals 3, you could have colored 3 with blue as well?
Yes. So here, there's no propagation going on with 1 plus 2 equals 3, because already there is one red and one blue over there. Yeah. But the 3 is forced to be read by the 1 plus 3 is 4.
1 plus 3 is...
So the 3 here, you have to forces 3 to be red.
Yeah, and the 4 becomes blue because of 2 plus 2 is 4.
Yeah.
Okay. Okay.
And so Sure didn't ask the question just for 2 colors. He just asked the question for all finite number of colors. So if you color the positive integers with any finite number of colors, is it always the case that you end up with a monochromatic solution of A plus B equals C? And the answer is actually yes. And so this is known as the Sure numbers. So for every positive integer k, there exists a number sk, also known as Sure number k, such that the numbers 1 to sk can be colored with k colors while avoiding monochromatic solution of A plus B is C, but this is impossible for 1 to sk plus 1. So this is what Sure proved in 1916, so over a century ago. And he was also able to show what is Sure number 1, 2, and 3 by hand. So Sure number 1 is 1, Sure number 2 is 4, and Sure number 3 is 13. However, it took half a century to actually find Sure number 4, which was also one of the early computer-generated results. So Sure number 4 was shown to be 44 in 1965. And in a paper a few years ago, I showed that Sure number 5 is 160. using SAT solvers, and the proof is enormous. So what I will tell you later on is actually that the proof systems that we've been using is actually trying to make the proofs as short as possible. But even in this kind of more compact kind of proof representation, the proof still is 2 petabytes in size. But we also have been able to verify it, which is also discussed later on. Now let's look at another problem, which is known. Sorry again for the structure. We are now asking the same question: can we color the integers with red and blue, such that we avoid a monochromatic solution of the Pythagorean triple? So, which is the equation a squared plus b squared is c squared. So, if you now look on the slide, I have all the solutions a squared plus b squared is c squared for a, b, c up till 40. And it's very easy to color them with red and blue to avoid a monochromatic solution. And this has been studied by various people, and till a couple of years ago, the best lower bound was coloring in red and blue of the numbers 1 to 7,664, such that there's no monochromatic Pythagorean triples. And Myers actually conjectures in his thesis that the answer is no. In other words, you can avoid this indefinitely. Now, how do we translate this into satisfiability? So what we're going to do is we're going to look at an interval 1 to n. We're going to look for a counterexample. And so we're going to have for each number in this interval, so 1 to n, we have a Boolean variable xi. If I is true, it means I is colored red, and if I is false, I is colored blue. And for each Pythagorean triple, so each solution for a squared plus b squared is c squared, we use 2 clauses, one saying that at least one of a or b or c is red, and the other one saying that at least one of a or b or c is blue. And together with Oliver Kuhlmann and Victor Marek, we showed that you can color the numbers 1 to 7,824 while avoiding a monochromatic Pythagorean triple, but this is impossible for anything larger. So the initial computation was 4 CPU years, but it was 2 days on the cluster back in Austin. And the proof was 200 terabytes in size, but it was validated using a SAT solver, for a verified checker. And not only did we...
So, Marijn, one question on the previous slide. So, so you need to enumerate the Pythagorean triples beforehand, right?
Yes.
Okay. And so this magic number of 7,824, was this by enumerating, or was it?
Oh yeah, and then let me talk about it a bit more. Yeah. So so proving that 1 to 7,825 is really hard. That was a lot of computation, but actually you can show that you can color the numbers 1 to 7,820. There's so 24. If you use a local search with the right heuristics, you can actually, there is one algorithm called DDFW, which can actually compute a solution for 1 to 7,824 in a minute. So,
oh, really? Okay.
Yeah. And so people have been trying
to get that number 7,824. So it tried out everything until 1,700.
Yeah, but so up till say 7,000, actually, if you give it any local search solver, it quickly finds a solution. And so what I did, but this probably that was I think done in say half an hour, is just, I just incremented things until things couldn't improve anymore. So actually finding the lower bound was the easy part. Figuring out, showing that you can no one step further, that was the difficult part.
Thanks.
Yeah. But if you use the right tools, because for example, Cooper and Overstreet, they have been using SAT solvers to get their best lower bound. But they didn't use, if they would have used kind of some older local search solvers, they would have been able to get to the actual bound. But yeah, it's kind of also surprised me that some of the older algorithms turn out to be extremely effective on this problem for the satisfiable case.
Okay, yeah, thanks.
Yeah.
Thanks, yeah.
Yeah. And not only, so I also tried, and that's my colleague might be interested in this. So I tried to actually enumerate or count the number of solutions for 1 to 7,824. But this is a daunting task as well. So what you see here on the slide is a big collection of colorings of the numbers, or of valid colorings. So the lower left corner is 1, and then if you go to the right, it's +1. If you go up, it's +100. So you can see also in the zoomed part here, any number that is colored blue must be blue, red must be red, and anything that is white can be either red or blue. And so the number of solutions that you see on this slide is actually already 2 to the power the number of white cells. And so at the point of 7,824, there are actually many billions of solutions. And going one step further, right, to 7,825.
What is the X and Y axis here?
So it's a visualization of the numbers 1 to 7,824. So the lower left corner is number 1. And so it's not
okay, got it, yeah.
And then it's number 2, number 3. It's just an ordering of the numbers.
Okay.
But Marijn, are you saying that the number 3 must be colored blue in all solutions, or this is a specific solution in which the number 3 was colored? I mean, 3.
No. So in this collection of solutions, 3 has to be colored blue. So, but there are many more of these kind of solutions.
So there are many more such colorings. That.
Yeah.
Okay.
And so this is one of the solutions that actually came out of our computations. But it's I mostly want to show that actually, in order to satisfy all the Pythagorean triples, lots of the numbers you don't need to color anything, right? Because in every triple there needs to be 1 red and 1 blue, and the other one, if you already have 1 red and 1 blue, the other one can be unassigned. And actually what you see is that there's so many numbers that can still be unassigned and still satisfy all the triples. Yeah, so, but because of course everything, if there's a solution with a number called, because if we would, all the numbers that are colored blue we would turn into red, and all the colors that are red into blue, right? Then we also still have a solution because the red and blue are interchangeable. Yeah.
Yeah, thanks.
Okay, and a third problem I want to discuss is some more recent work, which is Keller's conjecture. And now, so consider, so we have, say, the 2-dimensional space, say, for example, a floor, and you have all square tiles that are of the same size. And the question is, can you tile the two-dimensional space or the floor in such a way that it's not the case that two tiles fully share an edge? If you think about how to do this, then you quickly realize that the only way to tile the two-dimensional space is to put with equal size square tiles, is that you put them into lanes. The lanes you can shift them arbitrarily from each other, but all tiles within a lane, they fully share an edge with their neighbor. If you go now to the third dimension, and now you ask kind of the same question. So now we have the three-dimensional space, and now we have cubes, all of the same size. And now we also want to cover the entire space, so no gaps. Is it the case that we can avoid having two cubes having to fully share a face? And it takes a bit more thinking, but you come to realize that this is also impossible. So for example, I tried it on the image on the slide, but the blue faces, it's impossible to fully cover the space without having a fully sharing face for the blue ones. And Keller also observed this, and he conjectured that this would be the case for all dimensions. So for every dimension larger or equal than 1, every tiling of the n-dimensional space with unit cubes, it's always the case that there must be 2 that fully share a n-1 dimensional face. And this conjecture, so it seems kind of natural that, okay, this will probably extend. But the interesting result is, and that is what we finally settled, and there was also a Quanta article on this. So the conjecture holds for n is 1 to 7, but it doesn't hold for n is 8 and up. And what we showed, it was the remaining case, which was n is 7, and we also used massively parallel SAT solving to figure this out. So the encoding of this problem was much more complicated, and I don't have time to kind of go into detail here, but it also shows kind of what kind of that even this kind of tiling problems that SAT solvers can be effective in solving it.
So the space here is unbounded, right? I mean, n-dimensional unbounded space.
Yes, but in this, as soon as you have a counterexample for one dimension, then that counterexample also holds for all the higher dimensions. And so you need to show that it holds. So the paper kind of explains how the encoding kind of works. And there have been lots of, we kind of built on quite some earlier work that shows also how to discretize this, right? Because this is this conjecture talks about kind of continuous tiling, right? And how to make sure that you do this in a discrete way, because otherwise it's very difficult to express it for SAT solving. So we built on top of quite some earlier work how to kind of discretize this, and then we used that work and transformed it into propositional logic.
Okay.
Any other questions regarding the proof examples? Okay, let me continue. Okay. Well, so I used the word proof of unsatisfiability quite a bit, but let me kind of now go more into details. Already there was a question regarding satisfiability. So in case a formula is satisfiable, such as the formula shown below, it's very easy to check it, right? The only thing what we need is to give a satisfying assignment. For example, X is true, Y is false, and Z is true. And if we plug that in the formula, we go over the formula, check whether each clause has at least one green or satisfying literal, and then we're done. The difficulty here is when the formula is unsatisfying, right? So if the formula has n variables, we potentially have to check that all the 2 to the power n possible assignments falsify the formula, right? And this can be extremely costly. And so the alternative is to have some representation which is in many cases way more compact than the worst case 2 to the power n. And this is what we call a proof. So when I talk about proofs from now on, a proof is simply a string that certifies that a formula is unsatisfiable. And it's important that proofs can be checked efficiently. And that's what I mean is in polynomial time in the size of the proof. However, it can still be the case that the proof can still be exponentially large, right? We just want in case the formula, so if we have a proof, then we can check the proof in polynomial time in the size of the proof. And what we typically want more in practice is that in case the size of the proof should be kind of linear in the size of the runtime. So we want to have a proof that is kind of similar in length as the duration of the solving time. And most early work and most SAT solving techniques can be expressed using resolution, but also various things cannot be, and I will talk about that later. So what is resolution? So a resolution proof is a sequence of clauses, C1 to Cm, and each clause in this sequence is either occurring in the formula, or it can be obtained using the resolution rule. What is the resolution rule? It's you have a clause containing X, you have a clause containing not X, and you take their union and remove the complementary pair. So here C or X and not X or D. Resolution rule allows us to derive the clause C or D. And C in this case is a set of literals, and D is also a set of literals. And X and not X are just single literals. And if the last clause in this sequence is the empty clause, which we denote by the bottom symbol, then the formula, then we call this a proof of unsatisfiability. And there's this nice theoretical property that there exists a resolution proof for each unsatisfiable formula. Now let me give an example. So we have the formula on the top of the slide, and there is a resolution proof shown below it. Let me also show probably a much more convenient representation of that string is as follows. So we have the clause not X, not Y, or Z. If we resolve that with not Z, then we obtain the clause not X or not Y. If we resolve that clause with X or not Y, then we obtain the clause Y. If we resolve that one with not U or Y, we obtain not U. If we resolve that with U, then we obtain the empty clause. So by following this sequence, which is also described in the string over here, we can show that the formula F is unsatisfiable via some resolution steps. So it is a very nice proof system, and lots of things can be expressed using it. However, there are formulas which are seemingly simple, and for example, for anybody that kind of has seen this before, for example, pigeonhole formulas. Any proof for showing unsatisfiability using resolution will take exponentially many resolution steps. However, there are some solving techniques that can solve them efficiently. So what we would really like is that the proofs are kind of linear in the solving time, but if the solver can do things in linear time and the proofs are at least exponentially large, right? That means that there is a problem. Let me kind of, and so I will talk about this more in the second part, but so when we talk about a proof, it's actually simply a sequence of clauses. So a formula is a set of clauses, and this set is, each clause is denoted by a blue box. I will also use that same notation later on. So a blue box means a clause occurring in the original formula. And a proof is simply a sequence of clauses, each claimed to be redundant with respect to the formula, and the proof ends with the empty clause. Now, how are we going to check this? And I will talk this much more detail in the second part. How we're going to check this? We're going to check if adding the first clause from the proof preserves satisfiability. So if this formula was satisfiable, then the clause containing the first clause in the proof added is also unsatisfiable. And then we do the same thing for the second clause. Thus, adding the second clause to the formula still preserves satisfiability, and also for the third one and for the last one. And we know that the empty clause is unsatisfiable, and so by transitivity, the original formula had to be unsatisfiable as well. And what we want to do is we want to able to efficiently check for each clause that we're going to add to the formula whether it is actually redundant. So with redundant in this case means the very general thing is that if the formula was satisfiable before the addition, it's still satisfiable after the addition. Yeah? But in this notion, the empty clause is redundant for every unsatisfiable formula. However, you cannot easily check that it is redundant. So what we need to do is we want to add redundant clauses that we can efficiently check that there actually are redundant. And so what a proof is simply a sequence of clauses such that for each clause in the sequence, you can efficiently check that it's redundant for with respect to the given formula. Now the question is, okay, how are we going to do this efficiently? So I don't know whether you already heard about unit propagation. Unit propagation is one of the most powerful techniques in SAT solvers. What does it do? So we have, if a clause has length 1, so just a literal x, there's only one way to satisfy it, and it is to make the literal true. So you make x true. And if you make x true, so if there's another clause, say not x or y, so if you make x true, not x or y, the literal not x gets falsified, and the only way to satisfy it is to make y true. And repeating this until fixed point is known as unit propagation. And now we have the following definition. So given a formula f and a clause c, and let alpha be the smallest assignment that falsifies c. So alpha is, so if the clause is a or b or c, then alpha is not a and not b and not c. So it is the complement of all the literals in the clause. And so the clause is called implied by unit propagation. And this is how we denote this. If unit propagation on the formula, when we apply this alpha, this smallest assignment that falsifies C, results in a conflict. It's probably best kind of explained using an example. So we have another formula shown on the slide. And now we want to check whether the clause A or B is redundant. So let's check whether A or B is redundant. What are we going to do? We first pick the smallest assignment that falsifies C, which is A is false and B is false, which is shown over here. Now we want to do unit propagation. Does anybody see what unit propagation would do?
It has to set C to false.
Yeah, so here we have A and B are assigned to false. So the red literals show that these are false, green are satisfied. And the only way to satisfy this clause is to make C false. Now what happens next is that this clause becomes unit as well. And so we have to make D false. But after doing that, we have this clause A or C or D is falsified. And so we now have a conflict, which means that the clause A or B is actually redundant. And there's actually an efficient way of computing it using resolution. So if we start with the clause that was falsified, and we do the unit propagations in reverse order. So this was the clause that was last unit propagated. We have it over here. And we do resolution, we obtain this clause. The clause be unit propagated before that was this one. That's the one over here. If we do resolution, we obtain A or B. Yeah, and so you can check the redundancy, and so lots of clauses that are learned in SAT solvers are reverse unit propagation. And so the reason also for the name is that, so you first do unit propagation and then you do resolution in the reverse order.
Maren, is it possible to define it slightly more formally? What exactly you want to say by reverse unit propagation?
Yeah, so there is a more formal definition in the second part, where I also showed more examples. Okay. So this slide, I wanted to have it mostly the example, because otherwise the slide would be kind of full with techniques, the terms, but yeah, I will be more formal later. By the way, what? Yeah, okay. Because actually most I want to kind of talk here about going beyond resolution. So when we do resolution, for example, we have two clauses that exist in the formula, one containing X, one containing not X, and we derive its union without a complementary pair, right? And there's also another famous rule is modens ponens. If you have A and A implies B, we can derive B. And these are what we call kind of traditional proof systems. So everything that can be derived is logically implied. So you have rules that talk about if this is in the formula and this is in the formula, then we can derive that. This has its limitations. And so if you think about it more, is that everything that these traditional proof systems are doing is, so if you have this and if you have that, then you can derive something else. This is all reasoning about the presence of facts. So you ask, is this clause present? Is that clause present? Okay, in that case, we can derive this. But in order to kind of go have more efficient proof systems, we need to go beyond it. And what we're going to do is reasoning about absence. And so, again, so if this clause is present, if that clause is present, we can derive something that is reasoning about presence, right? What can we do if we reason about absence? And actually, you can do much more powerful things by reasoning about absence than if you only reason about presence. And this is also what we call interference-based proof systems. So why is this called interference-based? For example, if you have a formula with two solutions, reasoning about absence can actually, you can eliminate one solution or the other solution, which is impossible using traditional proof systems. But of course, you cannot eliminate them both at the same time, because then the formula would go from satisfiable to unsatisfiable. So if you reason about presence, you can, as soon as you learn something, you can you learn say X and you learn Y, then you can also learn X and Y. While if you reason about absence, this is not possible, not always possible. And so it might sound kind of a new way of thinking, right? Reasoning about absence, but actually reasoning about absence is kind of as old as SAT solving. And so one of the first rules actually in SAT solvers dating back to the early 60s is the pure literal rule. So the pure literal rule says that if literal not X is not occurring in the formula, then we can add the unit clause X. So you might have clauses say X or A or B, or X or C or D, but not X does not occur in the formula. Then you can learn the unit clause X. Note that if you learn X, this might remove solutions. So there might be solutions where not X, where X is false, but it is, if there are solutions, then there are also solutions when X is true. Another important result from the 60s is also reasoning about absence. And it's as follows. So it's the extended resolution rule. So if the literal X is not occurring in the formula and the literal not X is occurring in the formula, what we're then allowed to do is we can define X to be, say, the end of two literals in the formula, say A and B. So we can say, okay, we have a new variable X, which we say is the end of A and B, and A and B occur in the formula. And this, so adding this rule, so we have the resolution rule and this extension rule, is actually extremely powerful, and there's no lower bounds known for this system. And so you can have way shorter proofs in extended resolution than you can have in resolution. You can have exponentially smaller proofs using this extension rule. So it looks like one small rule that you can just add new definitions, but these definitions are extremely powerful in practice. Let me give one example. So, so the famous pigeonhole formulas.
Marian, just at a very high level. So, as you said, this is really defining a new variable in terms of existing variables, yeah. Right?
Yes.
Why does that lead to so much power? I mean, at a high level, is there some understanding?
Yeah, so let me
Does it
kind of
allow you to modularize proofs or something? I don't know.
So so I will talk about also on the next slide on the pigeonhole formula, okay. Right? So what you can do, so let me try to explain this on the next slide, and then if it's not clear, then I can go back.
Sure.
So the pigeonhole formula asks whether you can put n+1 pigeons into n holes such that there is at most one pigeon per hole. In the 80s, it was shown by Haken that all resolution proofs are exponential in n. However, Cook constructed proofs that are n to the power 4, and actually you can even make n to the power 3 proofs in extended resolution. So what are you going to do? So you have the pigeonhole with n+1 pigeons and n holes, and if you add definitions, you can say you can define the problem for n pigeons and n-1 holes. And because you can say, okay, if the pigeon, so the definitions say, okay, let me know where the pigeon is, and then I will move a pigeon in the last hole, the last pigeon in the last hole. And by making this change, you can reduce the n+1 pigeon in n holes to n pigeons in n-1 holes, and then you repeat this n times, and then you have whether one pigeon can be placed into 0 holes, and then you're done. And by making these definitions, you are allowed to kind of do what kind of a little kid would do for this problem, right? Okay, yeah, if it works for n+1, right, in n holes, right, then it should also work for, so the numbers just don't match up. And so doing this kind of inductive kind of reasoning is possible using extended resolution proofs, which is not possible when using resolution proofs. Because in resolution, you cannot say, okay, let's put a pigeon over here and then define the problem one step smaller. Yeah, does it kind of show a bit how this works?
Yeah, I guess, yeah. So it allows you to define sub-problems, or right?
So it allows you to kind of define new variables, right? And you can do this in such a way that from these new variables, you can derive the clauses that are of pigeonhole, the pigeonhole formula one size down. And then you just repeat this n times, and then you have the trivial unsatisfiable formula. So by defining a kind of a structure of the pigeons, you can derive the problem one size smaller, and then you just continue to do this. Yeah, so there's this paper from 67. It's actually I think it's only 6 pages. It's actually a very nice paper. So if you want to know the details, I would suggest going over that paper.
Sure. Yeah.
Yeah. So it is known that these proofs are extended resolution is extremely powerful. However, the main problem is how are we going to find such proofs automatically? Because the issue with defining a new variable is, okay, there are so many ways that you can define a new variable, right? There's the number of options is enormous. And so people have been trying it, but existing approaches to produce extended resolution proofs, for example, for the pigeonhole formulas, they turn out to be extremely big. And so nobody is able to kind of produce the Cook proofs automatically. And so we want to have this kind of strength of extended resolution, but we want to have it without kind of the necessity of introducing new Boolean variables. And is that possible? Can you make strong proof systems with reason about absence, but that don't really require to introduce new variables? And so there have been various approaches, and I won't be able to fully talk about it, but I just want to give you kind of the high-level picture here. And the first attempt here, and it's probably the most insightful one, is that of blocked clauses. Okay, let's talk about what are these blocked clauses. So a clause C or X is blocked on literal X with respect to a formula if for all the clauses containing not X, the resolvent is a tautology. So a tautology is a clause containing a literal and its complement. So in this case, say Y or not Y. Let me kind of explain this by an example. Say we have the formula A or B, and A or not B or not C, and not A or C. In the first clause is not blocked. Why is it not blocked? So there is no literal. So if we do, for example, look at literal A, we can do resolution with this not A and obtain a clause B or C, and B or C is not a tautology. If we look at B in this clause, we can do resolution with this not B, A, and then we obtain the clause A or not C. A or not C is not a tautology, so this is also not blocking. However, if we look at this clause and we look at A, the only clause containing not A is the one over here. If we do resolution, we get the clause not B, not C, or C, which is a tautology. And since so all the resolvents, so all the resolvents D or X, in this case, that's only this one, all of them result in a tautology. And so this clause is blocked on A. It's also blocked on not C, and also the third clause is blocked on C. Now, what is interesting now here is that if a clause is blocked, then adding or removing it preserves satisfiability or unsatisfiability, right? Depending on whether you add it or delete it. And so what we can do here, so is that we can remove this clause. And so if this formula was unsatisfiable, which it's not, right, then removing this clause would still keep it unsatisfying. And then removing this would also still make it unsatisfying. But we can also do it the other way around. Say we ignore, so we assume that this is our only, assume that this is our formula, right? Then we can add with block clause addition, we can, assuming that this is satisfiable, then we can add the clause not A or C. Now, to kind of give you an impression, why is this working? Why can we do this kind of reasoning? So assume that we have a satisfying assignment for a formula, and there is a clause which is blocked, say, on X with respect to that formula, right? But the assignment that we have that satisfies the formula but falsifies the clause. Now, so it falsifies the clause. Say the clause is X or A or B, and the clause is blocked on X. We know that X must be false, A must be false, and B must be false, otherwise the clause would not be falsified. Right? We know that all the resolvents with X are a tautology, so all the clauses containing not X also contain not A or not B. Otherwise, there wouldn't be a tautology. And by making X now true, this satisfies the clause X or A or B. And since all the clauses containing not X either have not A or not B, they must be still be satisfied. And so in case a clause is blocked, we can always turn a satisfying assignment for the formula and a assignment that falsifies the clause. We can turn this into assignment that satisfies both the formula and the clause. And it turns out that actually blocked clauses is actually a generalization of extended resolution. Because if you have a definition, say X is the end of A and B, if you carefully check this, then actually these clauses can be added by block clause addition. So these are the clauses stating X is equivalent to the end of A and B. So if we first add this clause, right, there is no clause not X, so this clause is clearly blocked because there are no resolution possibilities. If you afterwards add this clause, then the only resolution possibility is with the first one, which is, but if we resolve them, we get not A, not B, or A, which is a tautology. And the same thing you can do for the second one. And then again, it's a tautology, and so therefore you can just add them. So block clause addition is a generalization of extended resolution, and it's a generalization, but because also what we've seen here, we can also add a block clause which does not introduce a new variable. So it allows you to add the new variables, but also it allows you to do similar reasoning without new variables. And block clause elimination is can be used for all kinds of things. So it actually simulates many. If you have a circuit and you want to reason about the circuit, lots of optimizations that can be done on a circuit can actually be expressed using block clause elimination. And also for the Pythagorean triples, I will talk about it more. Hold on, let me see. I spent much more time, but actually for the Pythagorean triples, you can actually remove about 30% of the clauses by the same reasoning, which makes the problem much easier to solve. So I think it's about time now, right?
Yeah.
So
let me talk a little bit more about the next slide, and then I think it's so there's a lot of words here on this slide, and I will talk about it more later. So don't try to understand it, and I don't expect you to understand it. What I have here on the slide is kind of a description of the proof system that's actually used in the competitions, and it's actually used for all the proofs that I mentioned before. It is somewhat complicated. I will talk about it more later. It's called DRAT. And the only important thing for you to know is that if you, for this DRAT, is that it's an interference-based proof system, which can be efficiently checked. And also what it allows you to do is you are allowed to delete clauses. And the deletion of clauses, it sounds a bit strange, right? If you have you want to prove unsatisfiability, why would you delete clauses? But the deletion of clauses can be quite powerful in practice for various reasons. And so kind of that way I kind of want to conclude the first part, because I think it's now time for the break, right?
Yes, Kuldeep, you want to?
Yes, I think thanks, Maran, for the first half. We are going to take a 15-minute break, and then we'll reconvene at 7:15 Indian time.
Yeah. Can I have? Yeah. So one question. So because I actually was probably overly optimistic how fast I would go. So shall I talk about parallel proof production, which is the next part I have here, or shall I actually go to the slides I prepared for the second half?
I think, yeah, that's a tricky question.
Yeah, let's
solver to answer this.
Yeah.
Yeah, let me say go in 10 minutes, go over. Yeah, that's it. It's not easy to kind of cover this all. I guess I'm probably going to go continue with the with what I prepared for the second half, because it's also kind of more can give them hands-on experience, and then they can look at the slides kind of for the things I didn't cover. Because actually, I think it probably needs at least 20 minutes, if not 30, to kind of really kind of explain this in detail.
So were you going to explain DRAT in this part?
In the next part, I will go to explain DRAT.
Okay.
And here, this part is about how are proofs produced in practice, and how to do this when you do parallel computing. How do we construct proofs without knowing, without going into details, what the proofs look like in detail. So, for example, here I have kind of 5 stages how I made the proof for the Pythagorean triples. So first you do the encoding, then you kind of reformulate the problem to make it solve efficiently. Then you partition the search space, you solve the different parts, and then you produce proofs for everything, and then you validate the entire proof. And then I go into details about all these steps.
This would be very interesting personally for me.
Okay, let's see how fast I can go with the other one. I can come back to this if there's still time. Let me also take a break because I need something to drink.
Absolutely.
Okay.
Right. So Supratik, you want to put the banner for break?
Yes.
So Maran, maybe you can stop sharing your screen. I can, and we can. Yeah.
Okay, I'll be back in say 10 minutes.
Marian, I suggest we start 5 minutes late since we were 5 minutes late in ending the previous session.
Sounds good.
So maybe I can use the time to ask a quick question I had. In the slide just before we finished, you mentioned that block clause addition has the same generalized as ER, but then you are talking about block clause elimination. So I was just curious that it looks like the addition has more power, but then you seem to be highlighting that elimination is very useful in removing clauses.
Yeah, so that's we still didn't figure out what. On the one hand, so both of them can be useful, right? Both the addition and the elimination, right? And it seems to be kind of counterintuitive, right?
Yeah.
And it's still not clear which clauses you should add and which clauses you should remove, right? And in practice, what you do is you just eliminate all the blocked clauses and maybe add some binary ones back. But so the proof systems that are stronger than block clauses, and I won't be able to really cover them, but they tend to be more useful for addition. So, but what you can do is, so you first eliminate all the block clauses until fixed point, and then you only add those back which talk about the variables that are still there, right? For example, with the Pythagorean triples, lots of variables get removed by block clause elimination. And therefore you don't add anything back because all the ones that you removed, they contain at least one variable that is no longer present.
But elimination does not add any power to the proof system, right? Because
no.
So it's useful in practice, but addition is useful at least in theory, and we don't know how to.
Yeah. Because, for example, if you, so going back to this Pythagorean triples, so to the pigeonhole formula, you can add the definitions for each of the steps. So you can from n to n-1, n-2, n-3. And if you add all those definitions, then there's a linear size resolution proof.
Yeah.
However, what block clause elimination will do is they get rid of all these definitions.
Yeah.
And then there is the shortest proof is exponential. So we know that you can construct examples where block clause elimination will make things exponentially harder. But this is not what we observe in practice when you have instances, say, from the competitions or things like that. I'm not aware of any instance where that has been used in a competition or something where block clause elimination has been harmful. Although I can easily construct many of them. Yeah. So yeah, it's an interesting thing that is not kind of clear what's best to do, right?
Mm-hmm.
So extended resolution is adding block clauses, right?
Yes, It add blocks clauses, but only with new variables. Yes.
New variables. Now, if you do block clause elimination after that, all of those would go away and you'd be back to where you started.
Yeah. So if you do extended resolution without any resolution steps in between, then this will be the same as when you do block clause elimination. But as soon as you do add resolution steps, right, then block clause elimination is unlikely able to remove the definitions. So you say you have a clause X, so X is the end of A and B, but now you learn a clause containing X. After you learn the clause containing X, you are no longer able to remove the definition again with block clause elimination. Because the added clause might prevent you from removing it. However, in most cases, if you use red, which I haven't explained, but if you use red, then even if you learn the clause containing X, then red will still be able to remove the definition.
So I just wanted to mention, probably we can start the second half.
Yeah.
Sorry for interjecting. Okay, so I guess we are going to start the second half of the tutorial. Over to you, Marian.
Yeah. So yeah, so sorry that I was not able to kind of cover everything I was intending to cover in the first half, but let me continue because I've about the same number of slides for the second half. Let me try to cover that. But please also even I really would appreciate questions, right? I think it's much more important that people understand the slides that I cover than that I cover everything. So please don't hesitate to ask questions in case something is not clear. So the second part will also have an introduction. I will talk about proof checking and the proof systems and proof format. There I will go more into detail about DRED, certified checking, checking with a formally verified checker, and then I will talk about various applications and then conclude. So we've already seen this, so I won't talk about it much more, but there is this motivation, right? We need to really be able to check the results of SAT solvers because we cannot really simply assume that there are no bugs there. So this is a slide showing kind of a dubious honor. So when we solved the Pythagorean triples problem, we put the paper on archive, and then I was contacted by an editor from Nature that they wanted to do an article about it. And so I talked with her for 70 minutes and I tried to explain to her what I'm trying to explain to you is that SAT solving is cool and we can now really trust what's going on and we have full confidence in the results. And actually also we can do things with linear time speedups, something I was not able to cover in the first part. And unfortunately, none of that got into the article, only the enormous size of the proof, and that it was allegedly the largest math proof ever, which is kind of a dubious honor because it's so much easier to make it bigger, right? I really tried hard to get it as small as possible, and just making the heuristics work slightly less well, the proof will be instantly substantially larger. So it's not easy, not so hard to actually make a bigger math proof, just making worse heuristics. Okay, let me now kind of show you some demos, how this kind of works. Oh. So if you clone this repository, I don't know how many of you have done this, but if you clone this repository, then you have the files shown over here. There are 3 solvers there. It's glucose, lingaling, and catechol. And catechol is the most recent one. So glucose was the first one that actually had proof logging support, and then lingaling and catechol is one of the most modern solvers. And so in order to kind of get everything compiled, you simply, because I can show that. I won't run this because it takes a minute or two, but you just run build, and then you get all the executables that you need. One of them is catechol. Then if you then go to CNF, then there are a few files. So one of them is an equivalence checking problem or a hardware model checking problem. And so when you run a SAT solver, you typically, so you give it the SAT solver name, you give it the formula. And in order to produce a proof, you simply, although the DRED extension is not required, you just give it the second argument and give it a proof. So we're now going to run it. And it takes a couple of seconds to solve this formula. Oh, let me also, I will talk about that later, but let's first have it run to completion. Now, so it runs to completion, but the proof is in a binary format, which is very useful for storage and checking it more efficiently. But in order to show kind of how things work, I actually want to have the non-binary proof. So let me run it again and produce a proof which is non-binary. Yeah, and now so we have a proof, and now I can just look at the proof. And so what you see here, and I actually have not really talked about the format, and I will talk about it later, but actually the proof is simply a sequence of clauses, and I will explain later kind of what kind of these lines mean. Now, we have a tool called DRED Trim. There are also other checkers, but we can so this is the checking tool. This is again our formula that we just solved, and now we're going to give it the proof as second input, and it now is going now to check the proof. And so what you see here is that the proof has been verified, and it took about 10 seconds. So it was 20 seconds to solve the problem.
So this was an unsat formula, is it?
Yeah. Yeah, so exit code, let me see here, show you here, unsatisfiable. And so the solver was able to check it in 10 seconds. And so there are also kind of some interesting statistics here. Is if you look at this line, is so the formula itself contains 260,000 clauses. And but only less than 70,000 were used to prove unsatisfiability. So already these 68,000 are already unsatisfiable. Also, the solver learned 870,000 clauses, but only 153,000 were actually required during checking. Yeah. And so, and this is actually resolution proof, and it tells you that the number of that it was 2.6 million resolution steps were required to show incidence viability. So this is kind of this what the solver shows. The checker shows all kind of details about the checking, and it's these days it's very convenient. You just give so all of the top tier solvers, you just provided the second argument, and that is the proof file, and you can then give the proof file to the checker in order to kind of to check the result. So I will talk about more details later, but are there any questions kind of for this kind of high level kind of application of how to use proofs? It's very simple these days.
So the checker, I mean, for example, Dirac trim, the algorithm that it uses is it linear or quadratic in the size of the it's linear?
I think worst case it's quadratic, although on many cases it's in practice it's close to linear. There's also LRAD, which I will talk about a bit later, which is actually linear.
Oh.
But that requires more information in the proofs to make actually sure that things are linear. So now but I will go now into details of how things are checked. Wait, it is confused by having two talks. Let me view. Okay. Now, how to do proof checking. So already I mentioned the resolution rule, right? So if we have a clause containing X, a clause containing not X, we take the union and remove the complementary pair. So you can also equivalently, you can rewrite it using this symbol, this diamond symbol, which is the resolution operator. And frequently, when you kind of are going to check things, you use the so-called resolution chain. This is a chain of resolution steps. And the resolution steps are performed from left to right. But know that this is not associative. For example, so we have the clauses, the three clauses shown here on the slide. If we first do this clause, resolve it with, so not A, not B or C, resolve it with not A or B, and then with A or C, then we obtain the clause C. However, if we do it in a different order, not A or B, A or C, and then not A or not B or not C, then we obtain the clause not A or C. So if you have a chain of resolution steps, it is important to do the order right. Otherwise, you end up with a larger clause. Now let's look at how to kind of make compact proofs, because of course I mentioned already that the 200 terabyte proof is actually a proof that I tried to make as small as possible. So let me give some details why I actually consider it relatively small. So a resolution proof would actually, you can look at this as a graph. So the blue boxes are the clauses in the formula, and the red circles are the learned clauses by the solver. And so the learned clauses, they go from the lowest one is the first one that was found, and the last one is the highest one, and which is the empty clause. And in this visualization, and I will also use variants of this, the star means that there is a path from a clause to the empty clause. So only for not A, there is no path from not A to the empty clause, and that's the reason why A doesn't have a star. So what is a resolution proof? It is this entire graph. It is all the nodes and all the edges. So it shows so what the edges mean is, so the clause C can be obtained using resolution from all its incoming arcs. And we now don't talk about in which order, but all the incoming arcs allow you to kind of obtain C. And so a resolution proof is consists of all the nodes and all the edges in this resolution graph. And if you kind of run subsolvers on competition instances, then there is actually a crazy number of incoming arcs per node. So it's about, on average, about 400 resolution steps are made to learn a single clause. So each clause in the proof has about 400 incoming edges. And so since the number of edges is so enormous, storing the resolution proof, including all the edges, really increases memory consumption. Also because with resolution proof, you typically keep everything in memory. We also discussed.
I have a question here. So when you say 400 incoming edges, which means that 400 clauses are being resolved to obtain that resolvent clause, right?
Right.
But it could also have been represented, like maybe smaller groups of clauses, like binary. I mean, 2 clauses resolving to generate another resolvent. Right. So is there a trade-off here? I mean, we could reduce the number of edges coming into a node, but it will result in more. Like, for example, in the example that you're showing, I could resolve A or C and A bar or B to get B or C as an intermediate resolvent. And then I could resolve B bar or C and B or C to get C.
Yeah, but if you do that, then then you exchange edges for
nodes.
Yeah. And so then the number of nodes will substantially increase, right?
Yeah.
You may have options to reuse clauses, right? But that would probably also really require some heavy computation to really figure out which clauses can be reused if you would do such a thing. Because if you would do this naively, right, then you just exchange edges for nodes, and that is of any help. The size will still be the same. The size of the graph will still be the same.
Yeah, but you're saying that there is advantage to keeping these as edges and not as the intermediate nodes. Is there a reason you want to do it that way, or because?
So each of the nodes in the graph is just a clause learned by CDCL, right? Okay. And so if CDCL learns a clause, it's actually, so one of the reasons why CDCL works so well is not that you just do one resolution step at a time. It actually, the algorithm figures out how to do a large chunk of resolution steps at the same time to obtain a single clause.
Right. Okay. So these are clauses learned by CDCL.
That's, I think, the best way to view it for now. Most of the clauses will be learned by CDCL, but also all the clauses by pre-processing and in-processing are also of this type.
Okay.
but most of them typically have just 2 incoming edges. It's the CDCL that actually generates these clauses with 400 incoming edges.
Makes sense. Okay.
And so what is a clausal proof? A clausal proof is simply, we also store this graph, but we only store the order in which the clauses are learned. So, and we drop all the edges. So we're not describing any of the edges. We're just saying, okay, this is a proof. And so for every clause, there exist some edges that to justify that we can learn the clause. But we don't give it because, and that way, the size of the graph that we store is much smaller because we don't store the number, or we don't store the edges. So we just only store the nodes. Now let's have a look how this looks like. So in a clausal proof, we have the clauses here shown on the bottom, and we have the 4 clauses that have been learned. And so if we go from the lowest one first and then going up. So here I have them shown as a sequence, as I also did in the prior session. So we're first going to check not B, then not A, then C, and then bottom. So first is checking not B, and then we're looking, okay, can I find edges such that I can learn not B? And then the checker says yes by using the 2 clauses over here. I'm not talking about yet how to find them, right? But the checker is just okay. You ask the checker, okay, find me the incoming edges. And then I also do this for not A, just find me the edges. And then do it for C, and then I do it for the empty clause. And then since I was able to do for all of them, I was able to reconstruct the edges. I now say, okay, this is a valid proof. Yeah, so it's just, you go over all of the clauses in the proof, and you just simply check whether you can reconstruct the edges. This is, of course, not the most efficient way of doing it. And so I'm now going to talk about various ways to do this more efficient. So here you have a formal definition of how this, although it's also, but there's more details over here. So how are we going to reconstruct the edges? So I already talked a little bit about reverse unit propagation. So given an assignment alpha, so F under alpha denotes the formula without all the clauses satisfied by alpha and without all the clauses falsified. And what we're going to do is, in order to check whether a clause C is redundant, or in this case, the redundancy is actually implied by unit propagation, we're going to assign all the literals to false in the clause, and then do unit propagation, and unit propagation should result in a conflict. And all the clauses learned in CDCL have this property. And this property can summarize dozens or even hundreds of resolution steps. So let us go back to this example. So we're going to check whether not B is redundant. What are we going to do? We're going to make not B false. And so that means that B is assigned to true. If we assign B to true, right, then this clause becomes unit not A, and this clause becomes unit A, and together they form a conflict. And so we know it's, and then we can say, okay, not B can actually be learned. Next is not A. We are not A, we're going to make false. That means A is going to be assigned to true. Then means, okay, we can reuse the unit that we learned before, and together with, if we make A true, this also becomes unit, and then we have another conflict. The next one, we make C false. C false creates two units, unit clauses, not B and A, and together they falsify this clause. And finally, the empty clause, we assign it to false. There's nothing to do because there's no literals here. And indeed, unit propagation would just simply result in the empty clause. C and not B result in falsifying this clause. So we're going to reconstruct the edges by assigning all the literals in the clause to false, and then unit propagation should result in a conflict. Yeah. So this is the kind of the high level way of approaching this, but this is still very, very slow. So how can we improve things? So one of the most important thing is so-called backward checking. So say blue denotes the original formula and red is all the clauses that solver learned, one way or the other, with CDCL or pre-processing, it doesn't matter. And so the solver learns it, and at some point the solver learns the empty clause. And then we're unsatisfiable. So forwards checking would just check everything the solver has been doing. Is everything the solver has been doing correct? But that means checking everything in the red part is correct. This is not really necessary, because the nice thing about proof checking is that we actually can start with the empty clause and reason backwards. So we start with the empty clause and then think, okay, which clauses did I require to show that the empty clause, from which the empty clause follows? And then we can go back, and then maybe we only kind of need to check all the clauses in the green part. A nice additional thing about reasoning backwards is that not only you figure out which clauses in the proof did I need to check, but also which clauses in the original formula were required to prove unsatisfiability. And by reasoning backwards, you actually get for free a core of unsatisfiability, because you do the same thing, you just log everything that was required to produce the empty clause, and any clause in the original formula that was not used while checking isn't part of the core. And so backwards checking gives you this core, but also significantly improves the checking time. If we go, for example, back to what we did over here, right? The solver produced 870,000 clauses. But the checker, while doing backwards checking, only checked 153,000. So the red part is 870,000 and the green part is 153,000. Also, the blue part, the original formula, is 261,000, and the orange part, the core, is 68,000. Right? So this is how kind of the numbers kind of match what kind of is shown on this visualization. If you start with the empty clause, you can actually think about, okay, what is actually required, and then you can check only a part of the proof, and then also you can get a core from of the clauses that was actually is unsatisfying. So this is one of the most important kind of improvements for checking. And this was proposed by Goldberg and Novikov in 2003. And so what they do is you mark the empty clause and then you go do rep on the empty clause, mark everything that is used, and then go backwards and only check the marked lemmas. So the clear advantage is that you only check a subset of the number of lemmas. A disadvantage here is that it's much more complex to implement. Together with some co-authors, we also added some speed ups. The first one is actually to add deletion information. So the solver, SAT solvers do not only add a lot of clauses, but they also aggressively delete clauses. And if the formulas just keeps growing and growing and growing, and you need to reconstruct the edges, it becomes more and more expensive to reconstruct the edges because just of the size of the formula. But if you actually put also all the deletion information from the solver in the proof, then the formula grows and shrinks and grows and shrinks, and that really makes the search for the edges much more manageable. And so in the proofs, I also have these gray clauses now, and the gray ones, they denote the deletion of the clause. And it's so the proof at most doubles in size because you have to store the deletion information, but you can never delete more than you added. And but it can significantly improve performance of the checking. And this works as well with forwards checking as for backwards checking. You can use this clause deletion. And another important thing, what we did is we added this so-called core for first unit propagation. So so what we're going to do when we're checking, right, we make the clause false and then the unit propagation to figure out the edges. But with unit propagation, there are typically multiple clauses are units at the same time. And if there are multiple units, then you can choose which one you look at first. And the thing is that you can have much faster checking and actually a much smaller core by always unit propagating first on literals that you know that already must be in the proof. So you always avoid unit propagation on clauses for which you do not know whether they are really required in the proof. And so you keep postponing that, and that not only makes the unit propagation much more efficient, but also gets you smaller cores and smaller proofs.
So here, how do you get the core at first? Like in the first point, it says that clauses already in the core. So, but we get the core after generating the proof, right?
Yeah. So let me explain this on the next slide. I will give an example that I hopefully becomes clear. If it's still not clear, then I will go in more detail.
Sure.
So let me kind of explain how this works. Now we're going to do all the techniques that I discussed so far. So we're going to do backwards check. We have clause deletions, and I will also explain how the core business works. So what maybe before talking about the core, what will be the first step when doing such a proof checking? Anyone a clue? What would be a first step?
We should start from the empty clause.
Yeah, we're going to start from the empty clause, but before we're starting with the empty clause, we're actually going over the entire proof to see which clauses have been deleted, and they are removed. So all the clauses that have been deleted in the proof are taken away for the time being, and we put the empty clause in our core. We say, at this point, we only know that the empty clause is in the core. And now we're going to check which clauses are required to show that the empty clause is redundant, right? And so in this case, it finds C, not A or not B, and B or not C. And so it finds these incoming edges for the empty clause, and all of the ones with the incoming edges, they are now in the core. We now say, okay, everything that was required is just put in the core. Yeah, does that? And now we're going to go backwards, and now we go for C. We already know that not A is in the core, right? So we immediately want to reuse not A, because if we reuse not A, then we don't need to kind of extend things. But in order to get to show that it's unsatisfiable, the only we need to also have this second clause in there, because that's the only clause that becomes unit by making C false. And the interesting thing is, as soon as you hit deletion information, then you're going to revive that clause. So you don't do any checking, you just revive the clause. Now we're going to check not A, and the only way of getting not A is by using these two clauses, and they are just also put in the core. Now we're going to revive not B, and now we are going to check not B, but not B is not in the core, and so we don't check it. And so because we know it was not used for anything earlier, so we can just go out, skip it. And so now the proof checking is done, and we know that, okay, not B was not required in our proof, so it's not in our core of the proof, and not B or C was not required to in our formula. So the formula consisting of the 5 clauses to the right are now in our are unsatisfiable, and we know that we don't need not B or C to be unsatisfied. So is this now clear how the core works? So you initially only the empty clauses in the core, and as soon as you find edges, everything, all the ones that provide the edges, all the nodes that provide the edges are put into the core. Yeah, does it answer your question?
Yeah.
Okay. Thank you.
Marian, I guess it's a little tangential, but I wanted to ask that we want to revive the deleted clauses, but isn't it, originally the goal was that you want to be able to verify whether the answer is correct. And now we are also trying to verify whether the solver is doing correct steps, in the sense that why not revive empty clauses at the very beginning? Because,
what do you mean?
in the sense that we can, why not, when you start with the proof, everything that was deleted, you just ignore the information that the clauses were deleted. So are we using that clauses were deleted as a way to speed up the proof, or is it also necessary to be able to check the proof is correct?
If you only use plain CDCL, so no pre-processing and in-processing, then the deletion is only to speed up the checking. However, and so I will talk about DRED in a couple of slides. For DRED, actually the deletions might be required to make the proof working. And this might not be easy to see, but so if you recall about what I talked about in the first half, is that to get powerful reasoning, you have to reason about absence, right? And so, for example, you learn a clause X and say that it becomes, because so there is a clause, say not X or A, right? After you delete that clause, then X becomes a pure literal and you can add the unit clause X, right? And by adding deletion information, you actually can do some powerful reasoning afterwards. And that is only valid after the deletion, if you take the deletion into account. So for various steps in pre-processing and in processing, the deletion might be required, is required to actually check the proof. But for if you just stick to pure CDCL, then it's only about efficiency.
Oh, thanks.
Okay, now we come to DRED. So I briefly talked about it at the very end of last session. So let's have a little bit of motivation again. So we have these many simple formulas, but also not so simple formulas for which we know that resolution proofs are exponentially large. However, state-of-the-art SAT solvers can actually solve them in, say, linear time because they have dedicated techniques, but these dedicated techniques, it's impossible to compactly express them using resolution steps. So can we make a new system that actually can express all of these techniques that are used in these solvers in a compact way, and ideally that the proof will be linear in size of the solving time. And again, so this is a more high-level definition. At the final part of this slide, I will show the exact definition of RED. So what is RED doing? It is adding so-called RED clauses. I will define it below. So RED clauses, like pure literals or block clause addition, are not necessarily implied. Your reason about absence. And what we also know is, what need to know about RED is that adding RED clauses preserves satisfiability in the same way as block clauses or resolution preserve satisfiability. And this is new, and that is what I kind of just mentioned to Kuldeep in his answer. If you put in deletion information, you actually sometimes are able to do more powerful learning, because the deletion of clauses makes the formula smaller, and if you reason about absence, you can sometimes do more powerful additions. Okay, now what is the definition of RED? So it's shown here. On the next slide, I hopefully will be able to show you how it works by an example. But I hope that you can follow me to some extent. So a clause C or X is a so-called resolution asymmetric tautology, in short RED, on the literal X. If for every clause in the formula containing not X, the resolvent C or D is implied by unit propagation. Now, I don't know if, hopefully you recalled what the definition was of block clauses. So what was the definition of block clauses? We have a clause C or X, and for all the resolvents with a clause D or not X, all the resolvents were tautologies. And so red is actually very similar to block clauses, except for we replaced tautology by implied by unit propagation. And what we have seen, so all the clauses that we learned so far, right? Computing the edges is by you make everything false and unit propagation results in a conflict. A tautology is kind of something simple, right? If you have a clause containing Y and not Y, right, then you immediately have a conflict if you assign them both to false. But you can generalize this by saying, okay, everything that is implied by unit propagation works as well. Now let me explain this with an example. So again, here is the definition of red. Say we have these three clauses, and now we're going to ask, is C a valid red step? Now, what is the definition saying? Okay, so we know that this X over here should be the not C because there's only one literal. So it has to be that literal. Now what we're going to do is we're going to compute all the resolvents with the complement. So the complement C is only over here. So the only resolvent that we can have, C or D, is the not B over here. Yeah, and so this is the only resolvent, and now we ask, is this resolvent implied by unit propagation? And the answer is yes. If we make not B false, so we assign variable B to true, then this is a unit and this is a unit and we have a conflict. And so this clause is implied by unit propagation, which means that C not C is a D-red clause, of a red clause. And this is somewhat kind of surprising and actually very powerful reasoning, right? Because we have here three clauses over here, and none of them contains the literal not C, right? There's no clause containing not C. And now suddenly we can simply learn a unit clause not C while the clause where no literal not C is even in the formula, right? We have C in the formula, but we don't have not C, right? So it kind of seems crazy that you can learn literals or a unit clause from a literal that is not even occurring in the formula, right? So how this all exactly works, it's much more kind of complicated, but I really want to kind of give you kind of some feeling about how powerful reasoning you actually can add here, right? So we have three clauses, none of the clauses contains not C, and we can actually learn the clause not C because it is a resolution asymmetric tautology. Yeah.
It seems not unit propagation is like a reverse unit propagation. I not read.
Sorry, the sound is not really good.
Can you hear me right now?
Yeah, it's somewhat better, yes.
So when you imply the not B, it seems not unit propagation, it's the reverse unit propagation, right?
Yeah, reverse unit propagation, yes.
I mean, it's not equivalent to the unit propagation, right? Because I noticed that you mentioned in your statement to use the unit propagation, not to use the reverse unit propagation.
So implied by unit propagation and reverse unit propagation is the same thing.
It's the same thing.
Yeah. So implied by unit propagation means that reverse unit propagation, that unit propagation results in a conflict. If you assign everything to false in C or D, which in this case is not, you assign not B to false, which means you assign B to true.
Yes. Yes, thank you.
Yeah. Any other questions?
So, Amaran, so the point that you mentioned that C bar can be inferred, although it is not present in any of the clauses.
Yeah.
Right. Yeah, I guess this is. I mean, I understood the definition you mentioned, but this still sounds a bit discordant. I mean, where did it pop up from?
Yeah. So, but the property that red gives you is that, say, if we have a formula, if we have an assignment that satisfies the formula, so all the blue ones, but it falsifies the clause not C, then we can turn that assignment into an assignment that satisfies the formula and the clause. In this case, so we have an assignment that say we have C and not B, right? As in that satisfies.
Yeah.
That satisfies the formula, but it doesn't satisfy not C.
Yeah.
And because it's a resolution asymmetric tautology, we know that if we make not C true, then it is the case that the formula is still satisfiable. So not B or not C is also satisfying the formula. And we now satisfied not C. So we also always can change the assignment such that the formula and the clause can be satisfied. So if a clause is a resolution asymmetric tautology, if we have an assignment for the formula that falsifies the clause, we can turn this into an assignment that satisfies the formula and the clause. This is the property that you get if the formula is a resolution asymmetric tautology. Yeah. Yeah. So.
Okay.
Yeah. Let me. Shall I continue?
Yes, please. Yes.
Okay. Let me briefly give you kind of. So, if you to see how this works, so. This is our formula. So 1 stands for A, 2 stands for B, and C stands for C. And so if this is our formula and this is our proof, and we run dret trim on that, it actually says, okay, verified derivation. So everything that you added preserves satisfiability, although since it is not does not end in the empty clause, it's not a full proof. It just says, okay, everything that you added, so in this case, only the not free, the not C, is valid. Yeah. So this notion that we can also do clause addition and clause deletion actually kind of give us this proof system where we actually have two different kind of a different way of showing termination. So we start with a formula and we can learn clauses, and all the clauses that you learn need to preserve satisfiability. And you can also delete clauses or forget them, and then it should preserve unsatisfiability. And you can, in such a clause of proof system, which is a sequence of clause addition and clause deletion steps, you have two possible ways of termination. If you learn the empty clause, then you're unsatisfiable. And if you forget the last clause, so you show the formula is equivalent to the empty formula, then you're satisfied. And actually, if you have a satisfying assignment, you can easily turn this into a sequence of steps which removes all the clauses. Maybe for satisfiability, this is not, or for the SAT problem, it's not the most interesting way of doing it. But you can use the very same techniques for quantified Boolean formulas, where it's the satisfiable case is also difficult to check. And you can also use the same framework for richer logic, such as first order logic, where you show that the formula is unsatisfiable learning the empty clause and satisfiable by removing all the clauses. Yeah. Let me kind of continue here. So what I wanted to talk about more here. So there is kind of quite a history of these proof systems. So both resolution proofs and clausal proofs have been introduced in 2003, and they have their own strengths, right? So the strength of resolution proofs is that they can be checked very efficiently. And the advantage of clausal proofs is that they're very easy to kind of produce, and they're relatively small, right? Although, because you don't store the edges, right? The clausal proofs were without the edges, and the resolution proofs were the ones with the edges. Of course, they also have their disadvantages, right? Clausal proofs cannot be checked efficiently, and resolution proofs are difficult to produce, and they're also large because of all the edges. So over the years, together with co-authors, I made some improvements. So for example, we added the deletion, which really helped to speed up the checking, but also with the core first unit propagation and the other ones that I described earlier, things become way faster. The red clauses really allowed you to do the expressivity. All the techniques used in SAT solvers can now be expressed in this framework, and by combining it all, we kind of have all the properties that we would like. And another thing that we actually have now is that not only that we have all the kind of initial ideal properties, but we also have them now in formally verified checkers that are efficient and can check all these proofs now. So you already seen all these numbers. I don't know if you already played in an earlier tutorial with SAT benchmarks, but the format for SAT solvers is the so-called DIMEX format. And it starts with a header line, which is P, C, and F, followed by the number of clauses and the number of variables and the number of clauses. And each clause is shown on a line terminating with a 0. And the lines contain only numbers. Positive numbers refer to positive literals and negative numbers to negative literals. So if we have, for example, the formula shown over here, not B or C, we can turn the B, so we can use 1 for A, 2 for B, and C for free, C free, and then not B or C becomes -2 free. A or C becomes 1 free. Yeah? And so this is the format, input format used by the SAT solvers. And this is the input used by the SAT solvers, and the proofs will be kind of similar. So I want to go a bit more quickly here, because otherwise I fear I won't have enough time to go to the end. So the first kind of proof that was introduced was the trace check format by Armin Bieren. And so how does it work? It adds, so it first puts the formula in the proof and gives all the clauses in an identifier. So the first number in every line now becomes an identifier for each clause. And for all the learned clauses, we have the number of the numbers that correspond to the identifiers, how to make resolution between them. So clause 7 is the first clause that is learned in the proof, and it can be done by resolving the clauses 4 and 5. We do 4 and 5 is minus A or minus B, and A or minus B. If we resolve them together, we get minus B. Just kind of for the sake of time, let me kind of go over this relatively quickly. So there's actually in trace check, there's a lot of flexibility. So in the flexibility is that you don't need to, the lines don't need to be sorted. Because the checker is going to do the sorting itself. If you recall from one of the first slides of the second session, that having the resolution steps in order can make the difference, but the checker actually will figure out the ordering itself. And if you give the right ordering, then you don't need to list the clause, and you can actually abbreviate it also by giving it just the star. Okay, I think this is more important, so let me kind of spend a bit more time here. So what is a RIP proof? So we already discussed RIP, but a RIP proof is a sequence of clause steps, clause addition steps, and it looks very similar to the Dymex input format. So you just say, okay, learn the clause minus B, learn the clause C, and then learn the empty clause. And how does the checking work then? So we have our formula E as defined here above. So in order to check whether the clause minus B is valid, we check if you assign it to false, so B is true. If E and B is true, results in the empty clause. If that is the case, then we add not B to our formula E. Then we check whether C is redundant. We do this by making it false and checking whether it results, unit propagation results in the empty clause. Now we add C to the formula as well, and then the whole thing together results in the empty clause, and we are done. So the proof looks very similar to the input format of the SAT solvers. So on the one hand, that is an advantage, right? That, okay, you can actually look at the proof and you kind of try to understand what's there, right? Although, of course, with 200 terabytes, it is not really possible to really know what's going on, but at least you kind of have some feeling, you can kind of read it. The problem with that is that the proofs tend to be large, and one way of compressing the proof is by using a binary format, and which is actually the default for most solvers. Most solvers actually produce the proof in a binary format. And there are multiple ways of doing this. For example, you can sort the literals in the clause because the ordering of the literals is not important, except for the first literal, because the first literal is special because it is the literal on which a clause has the red property, if you use red. And so you can actually use, say, 4 bytes for a literal, then it gives you a small reduction. But you can also use the so-called variable byte method, which allows you to make even more compact proofs. And this is actually what is used in the competitions and by most solvers. I don't want to go too much into detail here. It's more to kind of make you aware that, okay, the proofs on the one hand can look very similar as the Dymex input format, but since proofs can be big, you might want to have a more kind of lightweight compression by using a binary encoding. And clause or proof checkers can produce additional results. And let me kind of show you some examples here. So you can produce a core of unsatisfiability, unsatisfiable core. We can produce a resolution proof, or we can actually produce a optimized proof. And let me kind of briefly show how this works. By the way, till what time do I have? I still have half an hour?
Yeah, a little more than half an hour.
Okay. Now, so recall that this is what we did earlier, right? We had this formula and the proof. And now I can say minus C core. That can be anything. I can also make it core file or something like that. And what it now does is it checks the proof again. And now if I open core file, it says, okay, now I have a formula which is of 68,000 clauses, and which is the 68,000 clauses subset of the 261 clauses. And we can now run catcall again on, say, the core file, and now new proof. And it's now solving it again. So remember that I think.
What is the color coding for? I mean, something showing up in magenta.
Yeah. So, but this is so our Mint solvers have the following kind of color coding now. It alternates between trying to prove that the formula is satisfiable and trying to prove the formula is unsatisfiable. So if it is white, the solver tries to prove it's unsatisfiable. If it is kind of this magenta, it tries to prove that the formula is satisfied.
I see. Okay.
So it uses different heuristics for the different modes. And so you might recall that it was, I think, 18 seconds to solve the original formula. And now if we just solve the core again, we can do it in 11 seconds. And the interesting thing is now, because we produced, so this is a proof for the smaller formula. All right, this is the smaller formula, and the solver found the new proof. Right? The interesting thing is, so if you have a proof for a formula, then that the same proof holds for any super formula, anything that's bigger. And so this is also what we can check, right? So we can use the proof obtained for the original, for the smaller formula, with the original one. And so we can just run this. And see, now we have the new proof, and actually the new proof was 500,000 clauses, but only 140,000 were used. And look here, our core file, our initial core file had say 68,000 clauses, but now with the new proof, we actually have 52,000 clauses. And so by making these new proofs and all this, you can get smaller and smaller formulas and smaller proofs. And actually, yesterday evening, because you can also use this is an option also in DRED trim, is really optimize it. This is aggressive optimization. This is very expensive, but I can quickly show you kind of what it's kind of doing. But it keeps optimizing the proofs. So it's now 140,000, but now it reduces it to 137, and it now keeps trying to do more aggressive techniques to try to make the proof smaller and smaller. This will take a while, and but for example, I did this yesterday evening till fixed point, and then that gives us this proof. And so this proof is actually say 47,000 clauses. So by just doing the optimization, you start with say the initial proof, I think, got 800,000 clauses or something like that, and you can actually reduce it to 47,000. If you
so as the reduction happens from one step to the next, it's a subset of the code that you found in the previous step.
Yeah, so so the techniques that I'm using is, so you keep the formula, but so during checking you also figure out what is the first step and the last step where a clause can be deleted. And this gives you actually flexibility. And so what I'm doing is I randomly put the deletion information in the proof in their valid interval. And this kind of, when you check it again, you really tend to find completely different kind of proofs, and that helps you to kind of reduce the size further. So I use the flexibility that you have when you can delete clauses to kind of optimize the proof further and further. And probably because this is, because I can also show you how this works. So I can now remove all the lines with deletion. And probably this actually gives us an even, so this it takes probably longer to check, but you see, so this gives you a slightly smaller proof also. So it can still remove a few, fix more if you completely remove deletion. So if you run, say, minus, I think, minus R, then you get resolution. Then you get a resolution proof. And for example, so here's the empty clause. It's not easy probably to see, but it's probably better to do it. So you learned the empty clause, that's the last part. And this is all the resolution steps that you need to take. These are all the identifiers of the clauses to which you have to take resolution. So, and if you go deeper in the proof, these lines are longer and longer. They will kind of be 400 on average. Yeah. And yeah, minus L is the one that, for example, you can get the shorter proof. And you get a shorter proof. Although, and so now you have the slightly shorter proof in optimized proof. Yeah, so these are, for example, a few things that you can do with DRED trim to get other results. Now,
maybe
yeah.
I can ask slightly kind of a high level question about the proof, which is how much are you interested in trying to find the proof that solver should have been working on, in the sense that how close you want the proof to approximate the behavior of the solver versus just being able to prove that the problem is unsatisfiable?
It is very difficult to figure out what the solver was actually, how the solver works, right? Well, what the solver was actually doing, right? Because you don't have the edge. If you have a clausal proof, so all the edges are not there. And I have been looking into the proofs that actually the edges that the solver produced and the edges that the checker produces, and they are completely different. I don't know whether that's a good thing or a bad thing, right? It's just what can be easily observed. And especially if you do the score first unit propagation, it seems that I think the proofs are better if you do this, right? But yeah, it's completely different. So but there's no way that you can really know what the solver did unless you store all the edges, right? So, and you can do that, but it also makes everything much more expensive. Yeah. So what we kind of want to do, right? Because so the solvers are heavily optimized, right? And that might produce bugs. So DRED trim is also heavily optimized with the heuristics and all the other kind of things. And so you might wonder, okay, why should I trust DRED trim, right? Why should I trust the checker? Because it's also optimized software. It's much smaller than a solver, but still. And so in order to have full confidence in the correctness, we have the SAT solver produce the proof, say our DRED proof, and then we have DRED trim produces an optimized proof, which is much smaller and contains all kind of hints, such that a formally verified checker can check it efficiently as well. And actually, there are now 4 different formally verified checkers, one in ACL2, one in Isabelle, one in COC, and one in KCML, that for which we can have very high confidence in the correctness. And so DRED trim can be a useful tool for kind of extracting all kind of information and also minimizing the proof. But what you actually want is to check the proof with a formally verified checker in kind of one of these, the 4 checkers that have been developed. Because DRED trim is likely buggy. It's not easy to kind of fool the checker, but I cannot promise that there's no bugs in there. But in order to have full confidence in the correctness, you better can have a formally verified checker. And this is also what, for example, what we are doing in the SAT competition. In the SAT competition, every formula is solved with one of the solvers. They produce a proof. Then DRED trim reduces the size of the proof and then the proof is actually checked with a formally verified checker to make sure that everything is correct. I also, for the sake of time, let me skip the kind of the part of how this formally verified checkers work. Yeah, because I think that's but let me talk about this. So if you want to do the verified checking, right, you want to, in order to make the tool the checking easier and also more efficient, you want to have the algorithm as simple as possible. If you want to have it simple, right, then you shouldn't do backwards checking, right? Backwards checking was very powerful, but it's very powerful for the first time, right? To kind of compute this green part in the earlier slide. But once you identify the green part or the smaller proof, then you can simply do forward checking afterwards. Unit propagation to figure out the edges is also expensive, and but the checker can actually kind of put hints where the unit propagation should be. And so that's what DRATrim is doing to kind of massage a proof for a formally verified checker. So it first removes all the redundancy. So only the green part is extracted, such that you could just do forward checking. And then it replaces the search for unit clauses by providing hints in the proof. So the combination, so the backward checking and the proof reduction really kind of make the proof much smaller. But then when you put in the hints, it becomes substantially larger again. And these kind of things kind of make that the optimized proof for the certified checker is about as large as the original proof. But we get the redundancy is just replaced by the hints. And we don't have to trust that this unverified tool says DRATrim. We don't have to trust whether that does anything which is okay, because if the optimized proof is considered to be valid, right, it doesn't matter how we obtained it, right? And so no matter how DRATrim obtained it, it should work. This new format is called LRED, which stands for linear red. So we can check red linear inside in the size of the file. So this was how our DRAT proof looked like for the small example, and this is how the LRED proof looks like. It is very similar to trace check, is that we have an identifier here for every clause, and we have the hints. And this says, okay, we do resolution with this clause. This is clause 1. And then we do unit propagation, and these clauses become units 2 and 3. So this is the clause that we do resolution with, and this is the ones that become units. And by having this integrated into the profile, the formally verified checkers can have a very simple implementation and be efficient. Okay, so say the last 15 minutes, I want to talk a bit more about some applications. So the proofs have been getting quite some media attention over the last couple of years. And one of the first ones was actually solving Erdős discrepancy conjecture. And so what is also the conjecture states that there exists no infinite sequence of pluses and minus ones, such that for all D and for all K, holds this equation. I won't want to go into detail about the conjecture because of the limited time. But when the authors solved the problem, the proof was 13 gigabytes in size in DRAD, and they checked it with DRAD trim. And this got quite some media attention, and so 13 gigabytes is apparently so about the size of Wikipedia. And so that is what kind of this is how things were framed, is that okay, the proof was as big as Wikipedia, and so that is impossible to check. I already mentioned the Pythagorean triples problem, right? It's 200 terabytes, so that was substantially larger than this one. But this was really cool that they not only solved it, but also that they, because the proof technology was kind of quite new back then, and it was really nice that they immediately started using it. So Dennis, so by the way, since you used a huge cluster, what you made parallelized? Yeah, so I was unable to talk about it in the first session, but actually both the proof production and the proof checking can all be done in parallel. And actually we can have linear time speedups even with thousands of cores. So otherwise this would be impossible. Otherwise it would either take years to do, or but the nice thing is that these techniques can be parallelized, both the solving and the checking. And so there are slides, so they will be posted on the summer of the winter school website. I think there are also some talks by me online that kind of more explain this also. So I think if you look at for other talks, then you can have the details. I won't be able to cover that now today. So, and if you're kind of, so the DRAD proof logging is now kind of supported by all the top tier solvers. And if you, for example, now run DRAD trim on the problem, so that is EDP, this is the formula, and this is the proof, and then this is say the output that DRAD trim gives you for errorless discrepancy problem. So it's kind of interesting that also, because it's a hard combinatorial problem, that you don't need all the clauses. For many hard combinatorial problems, you need typically almost all the clauses. And one of the nice things that also what they did is there are red steps in the proof, right? So what I just showed you with Catechol, there are only resolution steps, but the proof for the errorless discrepancy problem also had red steps, not only resolution steps. Yeah, and the red steps were mostly used to express symmetry breaking. Okay, that also brings me on. Oh, let me see.
So, Marine, slightly high-level question. So, for each of these problems, I believe encoding the problem is, very problem-specific. The encoding, and a naive encoding may not achieve the results, right?
Yeah.
So there's a lot that goes inside encoding as well.
Yeah, although for the Pythagorean triples and sure number 5, that the straightforward encoding works well. If we, for this problem, they actually invented quite a nice encoding. And especially so for the Keller's conjecture, we really needed to kind of use lots of tricks to kind of make a good encoding. Otherwise, it wouldn't have worked. Yeah. So this is one of the things that in the community, which still I think needs to be kind of, because it's making a good encoding is almost an art. And this is still not very well understood how to do this in general. Yeah.
Maybe if I can ask related question, have you noticed difference between encodings that make it easy to solve versus make it easy to generate the proof from DRET?
Yeah, so I was not able to cover it, but so what I typically do is I make the encoding as naive as possible when I started. And this is formula typically very difficult to solve. However, because the DRET is very powerful and you can do lots of things, and so I have also an encoding that is efficient to solve, right? And what I do is I express in DRET the modification of the naively encoded formula into the efficiently solvable one. And then that whole transformation is part of the proof. And so that way you don't need to trust that the kind of sophisticated encoding is correct, because you did a naive thing and then you just modified it such that you have the efficient one and you express everything in the proof, right? And so the proof checker just gets the naive version, the naive formula's input, and the DRET proof, which the first steps are actually turning in the transformation. Yeah, so that way you can kind of, you only need to trust the naive encoding, which of course you can still have questions about whether that's correct. But so for example, for the Pythagorean triples, this was just a C program of 7 lines, right? And if you stare at it long enough, you can kind of convince yourself, okay, that's probably correct. Another kind of problem that has been long open, and one of the kind of open problems in combinatorics is Ramsey number 5. So Paul Erdos famously joked about this problem. If aliens come to the Earth and ask us for Ramsey number 5, we should put kind of all mankind trying to solve it, put all computers on this, and we will be able to figure it out. But if aliens come to the Earth and ask us for Ramsey number 6, otherwise they will destroy us if we don't give it, we should spend all our money on military and preemptively strike. So what is this problem? So given a fully connected graph, if we color the edges with red and blue, is there always a clique of size k in red or clique of size k in blue? Or if we so the one that's the alternative that's described here on the slide is, if we have a graph of n vertices, is there always a clique or a co-clique? So a co-clique is an independent set of size k. So Ramsey number 3 is 6, and Ramsey number 4 is 18, and Ramsey number 5 is still open. Let me kind of briefly explain to you how Ramsey number 3 works. So we have 6 vertices, 1 to 6. And let's take the version where we color the edges red and blue. So we start with reasoning from vertex number 1. So it either has at least 3 red edges or at least 3 blue edges, right? Because there are 5 neighbors. So we know that there are either at least 3 blue or at least 3 red. And without loss of generality, we can say, okay, there are at least 3 red ones. And we can also say, without loss of generality, they are the neighbors 2, 3, and 4. Now, if we want to avoid a monochromatic triangle in blue, 2 and 3 need to be red. Otherwise, we have 1, 2, 3. 3 and 4 need to be read because otherwise we have 1, 3, and 4. And 2 and 4 need to be read because otherwise we have 1, 2, and 4. But if we have all of them, 2, 3, and 4 read, then we have a red triangle. So no matter what we do, we either have a blue triangle or a red triangle. So the SAT solver can also easily figure this out. But Ramsey number 4, if you do symmetry breaking, you can do this in about a second. And if you don't do symmetry breaking, it takes you weeks. And so one of the techniques that used by some solvers is symmetry breaking, right, which can quickly solve Ramsey number 4. We want this to be expressed in DRED, and then DRED can actually express symmetry breaking. So it can express what I just mentioned you, right? Red and blue can be interchanged. We have at least 3 blue edges, and we can assume that there are 2, 3, and 4. All of this can be expressed in DRED. It's not easy, but it can be done. And let me briefly give you a demo. Okay, so it might be one of the last things. So there's a verified checker also in the repository. It's called, there are actually 2 ones. Cake LPR is one of them. And if you give it Ramsey number 4 and you give it the Ramsey number, the proof, then the checker will say that the proof is correct, right? And so we now can, and I can, yeah, I don't want to go in detail here, but so we have now a formally verified checker that says that the proof for Ramsey number 3 of Ramsey number 4 is correct using DRED steps only. Yeah. Do I have slightly more time or shall I stop here? Because
I think yeah,
go ahead.
Okay, so one more problem I think is quite nice here also with the proof checking is the chromatic number of the plane. So how does this work? We have all the points in the 2-dimensional space and we have only one constraint. If 2 points are exactly distance 1 apart, then they must have a different color. And now the question is, what's the fewest number of colors that you need to color all the points in the 2-dimensional space? So reals by reals. So it's easy to see that you need at least 3 colors, right? Because there are 3 points in the plane with all distance 1, 1, 1, right? Such a, you can have a triangle and they cannot be colored the same. Actually, it's also not too much effort to show that you need at least 4 colors. So this is a graph, so known as Moser's spindle. It is 7 vertices and 11 edges, all distance 1. And this graph has chromatic number 4, and therefore you need at least 4 colors. It is also known, also since the early 50s, that you need at most 7 colors, because you can make tiles, hexagon tiles, with an outer radius slightly smaller than 1, such that so all the points within a tile don't have distance 1, and you can place tiles with the same color apart from each other such that the distance between them is slightly more than 1. So this was all known till the in the early 50s, and there was lots of people tried but did not make improvements. The only improvements came a few years ago when Aubrey de Grey found a graph with 1581 vertices that have chromatic number 5. And so this was the first breakthrough in many decades. And so he reached out to the media about his result, and the media reached out to Scott Aronson, who was a colleague of mine at
at UT Austin, and Scott mentioned, yeah, I cannot check this, but I think you can check it. And so, and I think that if it works, if you can check it, I think if Scott can check it, you're in an excellent position to improve on his results. So that's actually what I did in the weeks and months afterwards. So I checked his result, it was correct. And I used this with proof checking, but actually my proof checker gives us a much smaller proof, right? Because that's what the technology is doing. You can just ask, give me a smaller proof, and it gives you a smaller proof. So I think in a few days later, I was able to get his 1581 down to 74. And then in the weeks and months afterwards, I just got smaller and smaller proofs using proof trimming. And so how does this work? So I will keep it short, but how does this work? So we have a graph, and we ask, can it colored be with 5 colors or 4 colors? So if it cannot be colored with 4 colors, then so that is a proof of unsatisfiability. So we ask, is there the 4 coloring? And if the formula is unsatisfiable, then it's no. Then we can use the proof of unsatisfiability, and then we ask the checker, okay, give me a core. And all the vertices that are not mentioned in the core, they can be dropped, and we have a smaller graph with the same property. And by doing some kind of clever heuristics, you can get really smaller and smaller ones. And this actually gives you much smaller graphs than doing anything naive, right? Because one thing that you could do is, and that's actually what he did, is you have your graph with chromatic number 5, and then you take out vertices kind of in random order until you cannot remove anything anymore. That is actually, turns out, that gives you a very poor local minima. And by using the proofs, actually you get smaller and smaller ones. And so this is the result I published, what is it, 2 years ago? I'm now down to 510, but this is a graph with 529 vertices, which is based on proof trimming.
So Marayan, I mean, do you see some pattern in these graphs as you're reducing them, or?
Yeah, so that's the interesting thing, is that, so the solver is actually, if you look at, because this graph, there's quite some symmetries there, right? Although it's not, yeah, there are all, it's not perfect, right? But it's actually 2 graphs that are quite symmetric, and they are rotated slightly. But the interesting thing is that the solver, what actually the solver gives you back, looks quite symmetric, and that's also why I was able to get the smaller and smaller proofs. It kind of, I use the same kind of technique, but yeah, so it is, I think, one of the reasons why the SAT solver gets smaller proofs is also that apparently the SAT solver finds short proofs, and the shortest proofs actually typically are related to more symmetric graphs. Yeah, so there were all kind of cool things coming out of this kind of approach. Yeah, because my graph looks much more elegant than the graph that he came up with, yeah, by more naive methods. Yeah.
Yeah.
But yeah, so yeah. Did you have another question?
No, I just agreed with you. I said yes.
Yeah, but yeah, so I think because initially what I tried to do is to try to use some tools to kind of, some existing tools to actually try to proof kind of compute the smallest unsatisfiable core, because actually the community had made some tools to make small unsatisfiable cores, and all these tools work terrible. And so how these tools work, they were kind of similar as what Aubrey de Grey kind of did. So if you remove vertices or you remove clauses until you cannot do this anymore, then what you frequently end up with, you remove a certain clause, the formula is still unsatisfiable, but say it's first unsatisfiable with, say, 1,000 conflict clauses, and then you take out one clause, it's still unsatisfiable, but now it's now you take 100,000 clauses to prove unsatisfiability, right? And by doing this, by taking out clauses one by another, the proof tends to grow and grow and grow. Well, if you do the proof checking techniques that I've been using, that you don't throw anything away arbitrarily, right? If the proof checker says, I didn't use it, I have a short proof, and I didn't use this, right? Then there still is a short proof there, right? So you can throw these nodes away, and you still have you know there is a short proof because you have one, right? And by let the solver find new proofs, so you don't find the same short proof, but a new short proof, and then you throw away the other nodes that are not required, you shrink the graph more and more and more, while never come into the situation where you throw some clause away and the proof blows up.
There's a question.
So there's a question in the chat regarding the DRED proofs and the unsatisfiable cores by SMT solvers. So SMT solvers also, they use cores more, yeah. So it's similar kind of techniques, but they don't use DRED. So the proofs are more like resolution based ones. And then combined with the theories. But so the same, it's similar in nature, but I'm not aware of in the SMT world to have this kind of proof trimming techniques that have been implemented for SAT. So they give you a unsatisfiable core, but there's no techniques to kind of make the core smaller and smaller and smaller using proofs. Mate.
Yeah. I just had another question. That's all. If you're finished with this one, then I have another question.
Yeah.
Yeah. So I mean, it feels to me the flexibility of the RAD system is that it's not a prescriptive system that tells the proof verifier that these are the exact clauses I used to find this clause as a resolvent, but instead the DRAD proof effectively just says, well, this somehow came out of the set of clauses that are currently in memory, do your best. And so you're sort of using this to your advantage to minimize proofs. I mean, this is one of the things that you use, right? And so my question is that, have you played around with because of course it's a sort of a heuristic, maybe somewhat random, that the DRAD trim system uses to pick which clauses will, it will pick to create this resolvent, and ostensibly there possibly could be a way of using a different set of clauses and using a heuristic for picking the clauses that I'm going to resolve to come to this resolvent. And have you played try to play around with the heuristic that the DRAD trim system uses to pick which clauses it will use to create the resolvent, and does that make a difference?
Yeah, so I'm not sure whether you were at the earlier part of this talk, but so this core first unit propagation, this is the main heuristic that helps. So you prefer unit propagation on the clauses that already will be part of the proof. And that really speeds up unit propagation, but also gets you shorter proofs and smaller cores.
Okay, sorry, no, unfortunately I couldn't participate at the beginning. Okay, thank you. Yeah.
Yeah. So, but this is so yeah, so I have an FMCAT paper on these heuristics. So if you want to know more about the details, and this is important too. And what the other thing that I'm doing, so if I run it multiple times, because the unit propagation is also depending on the literals ordering, and so I shuffle in every step. I shuffle all the literals in all the clauses. And that actually gives you a different proof next time around, because based on the ordering of the literals, you get different unit propagation order, and that also yeah, because the first step you
using this tool.
Oh yeah. Okay. Yeah.
We're using the optimization as well for our for some of the tools that we're developing. Yeah. So yeah, it's very helpful. And I saw that you shuffle the literals, and I was expecting that you were doing that for to increase the randomization and effectively arrive at a different proof. If I understand correctly, that's the idea.
Yeah. Yeah, because that's so. Because you don't have the edges, right? You actually a DRED proof is actually covers many potentially resolution proofs that you can have, right? And you just ask the checker to give you one of them, right? And to try to find a short one. Yeah. Okay. Any other questions? Okay, I'm not sure whether there's much more. So there's the conclusions. So far, I only showed some of the things that you can do with DRED trim. If you run DRED trim -h, there are multiple other things that you can do. For example, you can turn off this core first unit propagation, and you will actually see that the performance gets way worse. You can also turn off the backward checking, which also makes things worse. And typically, you can have a progress bar. And this is what I don't know if you've seen this, Mate, but this -0 really optimized it until fixed point. And
yeah, I use that with -0. You can even pass a number in numerical, and it will try to optimize a certain number of steps. I think this goes to fixed point, but I only use it a number of steps. But yes, this is very helpful. Actually, it's very interesting to see the proof shrink. It's really cool. I suggest people check it out.
Yeah. So this was the main technique that was used also for the chromatic number of the plane, right? I also did this optimization of the proofs. Yeah, and then I have so some conclusions. So the verification of proof of unsatisfiability is now mature. So kind of all the top tier solvers support it. There are formally verified checkers in ACL2, Kok, Isabel, and KCML. The proofs are kind of now more and more used for problems in math, but also in industry. The competitions use it, and I think one of the core things is that there's quite a little overhead, at least to produce it, and the checking, I think, is still reasonable. What are the challenges? So 200 terabytes is still quite a big proof, right? So how can we further minimize the size on disk? This is not easy. How can we minimize? So the proof checker sometimes use quite a bit of memory, cannot be reduced. And what other information can be kind of mined from the proof? So we talked about optimizing proof scores and crack interpolants or things like that. That what can all be done, right? I think there's lots of potential here. And although this is now posted as kind of a challenge, but we have been making quite some progress here, and mostly Randy Bryant has been making a lot of progress here. How to kind of do Gaussian elimination, cardinality resolution, and pseudo-Boolean reasoning. And we think we're getting close to kind of make a very good way of doing this. And also Mate is involved now in the Gaussian elimination part. And so I'm hopeful that we can actually solvers that use these techniques, that we can efficiently generate DRED proofs from them. So we know it can be done, but how to do this elegantly and efficiently. So that concludes my tutorial. Any further questions? If not, many thanks for attending.
Okay, I guess there have been questions throughout the tutorial. Thanks a lot, Marijn, for this excellent tutorial. Also waking up so early in the morning. We really enjoyed the tutorial in our convenient evening hours, but thanks a lot again for waking up so early.
Yeah, I'm happy to do it. And so I noticed a few typos in the slides, so I will fix them and send you the final slides.
Yes, that would be great. We'll be able to upload it online. So let's thank Marijn again for the tutorial. Maybe I'll clap on behalf of everybody. And that concludes our day 2 of the winter school. We'll be meeting tomorrow early morning at 9 o'clock. So we have about 12 hours to recharge ourselves. I guess I'll leave up to you to close the day.
Yeah, sure. I think you are the host, Kuldeep, so you have to. You're the host of the Zoom meeting.
Okay, so I'm going to, I guess, end the Zoom meeting.
Yeah, thanks, Marijn. Yeah, amazing tutorial.